This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, so welcome everyone. We're going to make a start, and thank you so much for joining. It is really exciting for me to finally be at this stage. It's been a long journey, and I'll tell you about that journey in a minute. But before that, I'd just like to acknowledge that we are on the lands of the Wurundjeri people, on the Unceded lands. I want to pay my respects to the elders past and present and any Indigenous peoples here today. And I want to say that the Indigenous peoples have always been making discoveries and sharing knowledge as we are today. So this is the first OPM-MEG workshop of what I hope to be many more workshops over the years to come. And as I said, it's been a long time coming, exactly 10 years. Since I had a dream. And a very famous Portuguese poet says that the dream commands life. And so I think that is true. You start with a dream and then things unfold. So let me start with the history of OPM-MEG in Australia. And then I'll move on to explain exactly what are we talking about, what can we measure, what is it good for, and I'll do a very brief introduction of that. But then we'll have Sophie, Lynn, who's there, and Holly Schofield from Nottingham. Sorry, I should say Sophie Lynn is based at the University of Melbourne, for those of you who don't know her. And Holly Schofield is from the University of Nottingham, all the way in the UK. So we're very, very lucky to have her here in person. We will have Team Tierney from UCL. That talk is going to be online. And we will also have some hands-on sessions in the middle of the day while afternoon tea is happening. So we will have 5 groups, and if we will call your names for the individual groups, and the first group will go to the hands-on session while the others can mingle, make friends, and eat a bite, and then we'll keep doing that until the last group is all done, and then we'll reconvene here for Holly's talk. So. That will be sort of the overview of the day. So here it is. This is what it looks like. That's our system in Melbourne. You will see it, for those of you doing the hands-on sessions, you will see this in real life. And there's, as I said, it's been a 10-year long journey. And in the beginning, there was Gareth Barnes at UCL. I've spent many years at UCL, in fact 7 years between PhD and a postdoc, and I've worked a lot with Gareth using the cryogenic MEG, which is the normal, or the one the conventional MEG. And so as I went back to see some of my colleagues at UCL, I met Gareth, and he said, Marta, you've got to see this. And what he had was MEG data with OPMs, and it was really clean data, and it was a lot better quality and better signal-to-noise ratio than the cryogenic MEG. And I was pretty much, that's the description of my excitement in that photo. And Gareth was very, very excited as well, of course. He had been working together with Matt Brooks in Nottingham who is Holly's supervisor, working very closely, and so those two have been really at the forefront of developing OPMs for MEG for a very long time. And so then I was very, very excited about it, and I kept wishing there was something like that in Australia. But anyway, that idea just stayed in the back of my mind, and then lots of things happened. In the meantime, so this started 2015, as I said, and then 2016, I started my group at the Queensland Brain Institute at the University of Queensland. Then I had my second baby. Actually, that first meeting with Gareth, when he first showed me the OPM data, I had my first son, who was a toddler, running around, and I was just trying to have a meeting with Gareth and seeing the data while, you know, there was this chaos. Anyway, then 2019, I moved to Melbourne Uni, where I've been ever since. But throughout this time, these ideas of bringing OPM-MEG to Australia, they were still in my mind. So then 2019, I've requested funds from the Centre of Excellence for Integrative Brain Function, which is now, that centre is now finished. It was a 7-year period, was fantastic. And with support of Gary Egan from Monash University at the time, was the director of the centre, we were awarded a little bit of funding to purchase 2 or 3 sensors, 2 or 3 OPMs. And that's what they look like in that picture. You see they are really tiny. And also at that time, I also recruited Sophie Lynn. I was really lucky to convince her to move from the UK. I believe you were in between Birmingham and UCL at the time, right? And I knew we needed somebody with the expertise who actually knew how to do OPMs or measurements with OPMs. I had done a lot of cryogenic MEG, but not OPMs. And so Sophie was convinced to come. And that was pretty exciting. I had the person, I had a couple of sensors. And then 2020 happened. And we all know what happened. It was tricky for all of us in many ways, and but particularly for those of us doing human experiments, all of that was halted, and so we couldn't really go to the lab and get this happening. However, in between lockdowns and being able to go back into the lab, Sophie and Will were able to work together, and we did the very first OPMEG recording in Australia. So that was sometime in 2021. You might remember the month. November. There you go. November. So we were very, very excited. And it is important to mention that this was done in the magnetic shielded room at Swinburne University with the support of Will Woods, who was based at Swinburne, because for OPMs we still need a shielded room, and we didn't have one here. Those things are very, very expensive. To be precise, $1 million expensive. And so they were very kind to let us in. But not just that, to really help us to bring the noise inside the shielded room to a lower level that is required for OPM. So the OPM requirement for shielding is even higher than it is for cryogenic MEG. And so there was a lot of hard work, mostly from Sophie and Will, to get us to that point. And you see how the data looks like. I think it's beautiful. I'm always excited when I see a mismatch negativity response. I've been doing that scene for over 20 years, but it gives me a kick every time. And so there we are, we've got an MMN, I'm pretty excited. And that, at this stage, I thought, well, we can do it. We can actually do it. So maybe we can convince the funders that we can scale this up to have a whole head system. Obviously, this is all very, very expensive, so I had to go knocking on doors, and I knocked on many, many, many doors. Eventually was able to convince 13 CIs, Sophie is one of them, to come in on this application together. There's 7 universities involved, and all of them contributing with cash. So as you might imagine, there was a lot of negotiation and campaigning that this was a good idea. So 133 pages exactly later of an application, and $2 million, what ended up being a $2 million system when factoring in all the constructions, with $1 million coming from the ARC and the rest co-investment from the different universities, and mostly from the University of Melbourne. We put together this application, and at the time we proposed different types of areas that we wanted to go towards, as you see there. But really, this is just a starting point, because it is a capability that is there to be used for any question that you might have, and which is suitable to be answered with that machine. So a few months later, we received the amazing news that we were successful. Our grant was awarded. This was pretty exciting. This was 2022. OPM-MEG was coming down under finally. Lots of people in Australia were excited, but also it was very heartwarming to see lots of our colleagues in the Northern Hemisphere really happy for us that this was happening. So there was a lot of Twitter love at the time. So 2022. Making it happen, it wasn't as exciting, let's put it that way. It involved a lot of hard work, more hard work again. So it took about 2 years to have many, many meetings with the engineering team, the building and infrastructure team here at the University of Melbourne, architects, commercials, legal, providers. From the time we put in the grant and we had a quote to the time we approached the providers again to say, hey, we got this, we want to go ahead. Of course, prices went up. So we had to go back and forth and try to get more funding from different places. Then a lot of paperwork to do with OH&S, health and safety, SOPs, system booking, you name it. A lot of work, and a lot of it thanks to Sophie, but also a massive team in the university of people who I didn't even know, and in the beginning with language that I didn't even understand, trying to understand, the different language of the infrastructure team and the legal team. So anyway, it's been quite a journey. The magnetic shielded room was eventually installed by Cerca in July 2024, so a year ago. The sensors were installed just a few weeks later. So just the magnetic shielded room actually took 3 months physically to put together. I don't know how many of you were here. A few. A few people physically building putting all the things together. The sensors took just over a week to connect up everything. And then a few months of beta testing, checking the data was fine, a lot of piloting and so forth. So 2 years and $2 million later, we haven't actually done any research, nor do we have the money for it. So it's been really, really interesting journey, but now on to do the actual research. That is the fun bit, right? So just some photos of what the shielded room looked like when it was installed back a year ago. You can still see bits of the construction bits left behind. Now it's looking a lot neater, and as you will see. And this is the photo taken in August last year. I was pretty excited to be in there. And you will see all of this when you go into the lab and have your hands-on sessions. Can I suggest the people who are standing their seats at the front if you'd like to come? Thank you. Just don't want anyone to be uncomfortable. Okay, so we've got 50 sensors over this helmet. And that is a pretty good start. Hopefully we'll be able to scale this up to 144, which is the max that we can go at the moment with this type of setup. Of course, it just costs a little bit of money. And then data finally. So we had our first community participant. After all the piloting and all the hard work, we finally were ready to go. We have funding from a philanthropic foundation to run a big study looking at schizophrenia and psychosis. And there's a lot of stars here, Elise Rowe, Tracy Colgan, and Lila Nateg. They are sitting there. Can you put your hand up or stand up so everyone can see your faces? And Sophie, this is for you too. So all these 4 people, sorry Sophie, I should have told you to stand up as well. I feel like I need a face of you in every slide because none of this would happen without you. So with the help of all of these people, we were finally able to have data. This is again a mismatch negativity study with beeps and boops, and it's there, it's beautiful, and it's working. So very, very exciting. Another study, just keeping an eye on time. Another study that is happening at the moment is led by Sophie. It's looking at cerebellar activity. The cerebellum has been notoriously, in a way, difficult to study with MEG because of not enough coverage. But also, for a long time, people, for some reason, didn't really care about it. So we would see it in fMRI light up, but people would be like, oh well, nobody would really care about it. But that has changed finally, and we know that the cerebellum is evolving all sorts of interesting functions, like memory and emotion and predictive processing. So this is something that Sophie mostly is driving here in Melbourne. So I'm really excited to see what where this leads us, and you can see the data is there as well. And you can ask Sophie more details about this experiment later on. We also have 5 other projects about to start. Natalia is leading one of them. Jacob is leading one of them. Daniel, I don't think I can see him here, but he's leading another one. And there's another project with the Faculty of Engineering as well about to start. So very excited to see that kick off the ground. And also your project is next, so let us know if you get it. I hope you all get excited about this technique and that at the end you wanna use it too. So now I've been telling you about the history of, and it took 10 years, this is a summary of the past 10 years of me thinking about bringing OPMs to Australia and managing to excite lots of people about it. But what exactly are we talking about? So I think this slide is useful to put MEG into context of the other imaging techniques. Of course, MEG measures magnetic fields generated by the brain. And we've got lots of different brain imaging techniques, and they're not all in here. Some of us were just at the Organization for Human Brain Mapping meeting, and there's more techniques happening or being developed all the time, and so there's a few that are missing from here. But let me highlight the ones that we use mostly in Melbourne. So there's EEG and fMRI. Some of you might use PET as well. But and MEG is here. So this slide is useful because it shows us where MEG is in relation to the other techniques with respect to spatial and temporal resolution. And you can see for temporal resolution, it is absolutely the best you can get, just as good as EEG with millisecond resolution. When we look at the spatial resolution, you can see that there is an improvement quite significant from EEG to MEG, so with MEG being having better spatial resolution, both at the scalp level with less distortion of the signals, but also when you go to source, you have a much better spatial resolution, and you can see here for reference what the spatial resolution is for EEG and for MEG respectively. Of course, spatial resolution of MEG is not as good as fMRI. It will be hard to beat, but it does have that optimal compromise between spatial and temporal resolution. So if your question is about where and when in the brain, and you want to answer that question really well, then MEG is your technique. If you just care about time, when in time certain processes happen, then EEG is just as good and cheaper, so in fact it's better. If your question is just about where, then fMRI is your technique. But yeah, if you want both, then MEG offers the best compromise. So what are we really measuring? So we are, as I said, we are measuring magnetic fields. Is this a sign that I should shut up? I'm okay with the lights on. Can people still see the slides? Okay. I still have time. Okay, but it is important to know that we are not measuring action potentials. We are measuring synaptic currents, and we are measuring the synaptic currents that result from the activity of many neurons, all lined up together in the same orientation. That's the only way where we can have a signal that is strong enough to be captured at the scalp level. Now there is a big problem, and the big problem is that the brain signals, the magnetic brain signals are tiny. So to be precise, about 10 billion times weaker than the Earth's magnetic field, and that is a pretty big problem to get around. So for context, again, taken from Matt's paper, is this plot over here. You can see the strength of the magnetic field of the MRI scanner. On campus, we've got a 7T, and you see it's pretty high. Then we've got the Earth's magnetic field is lower. Then we've got magnetic fields generated by trams and trains passing by as they move, and we've got magnetic fields generated by your heart. And then finally, we've got these tiny neuromagnetic fields generated by the brain. So you see it's several orders of magnitude smaller than all of these signals that we've been talking about. And importantly, a lot smaller than the Earth's magnetic field. But we are on Earth, so it's hard to get around that. So how do we get around it? We get it to, we don't, we get it to go around us, essentially. And I'll show you in the next slide how we get it to go around us. So we have a magnetic shielded room that essentially shields the space inside from the external magnetic fields that we don't want. That is the Earth's magnetic field, and mostly does a good job of vehicles passing by. So you see the lines of the magnetic field kind of go around the box that we have of the magnetic shielded room. We also use very sensitive sensors, and what you see here, they are squid sensors. These are used in the cryogenic MEG, or the standard conventional MEG machine. These sensors are fantastic, but they operate at a very low temperature, and that creates some issues. And one of the big issues is that these squids have to be in a bath of liquid helium, and for that to happen, we need precisely for the temperature to be minus 269 Celsius. So that is very, very, very cold, right? Because it is so cold, we can't have the sensors that close to the head because it will freeze the scalp. We can't do that. There's helium refills every week. That is expensive. And I mean, I should actually start to say, I still love this this machine. It is very, very useful. We've learned a lot from it, but it does have limitations, and these are the limitations that I'm pointing out. There's been helium shortages around the globe. I think it's a little bit better now, but there were times where the cryogenic MEG systems weren't operating for a period of time. And of course, there's environmental implications as well, because it is a limited resource. The sensors, as I said, they have to be not that close to the head. They have to be at least further away than 3 centimeters. And that limits the signal detectability, because the magnetic signal decays very rapidly with the distance. So if we've got a source here, the further, of course, the further the sensor is, less signal we capture, and it turns out that it decays very, very rapidly. So that is an issue as well. The head must be very, very still. So we ask the participants to be as still as possible. We put padding in to help the participant stay still. But the criteria to use data is that participants can't move more than 5 millimeters. And that is very easy to do, unfortunately, or the other way, it is very hard not to move that small amount. And unfortunately, if that happens within a run, we essentially have to discard that run altogether. As an experimentalist, that has happened to me, and that is quite frustrating. But also, it's a waste of data. Also, it is rigid and immobile. So you see, it is quite overpowering thing, and because of its rigidity and the fact that we can't really move much, it limits the type of populations that we can scan. So for children, we actually need a completely different system that has a smaller head size. So that's what Macquarie has. Macquarie University has an adult system and a child system. So of course it's expensive to have a second one. I mean, it's expensive as it is to have one, let alone two. But also there's people who struggle to sit still. And of course, children are one example, but people with movement disorders like Parkinson's disease. And we'll hear about Parkinson's later on. So all these pose some limitations as much as amazing this technique is. And so with OPMs, we can go around all of these problems because it is room temperature, we don't need helium, so it becomes a bit cheaper. Because it's room temperature, in fact, it has to be slightly warmer than room temperature to work. They can be put closer to the head, and that improves signal-to-noise ratio because, again, the signals decay very rapidly with distance. So getting that to 2 centimeters closer, it's actually a massive improvement in the signal. And you'll see in the next slide how much of that improvement we're talking about. And it is flexible. It accommodates any shapes and sizes of heads. We all come in different shapes and sizes. We are all beautiful and scannable. That's what OPMs are saying. So regardless of shape and size, we can do it. And it is robust to movement. So that means that this technique can really take off and get us to more naturalistic types of paradigms. So how does this work? So I won't go into the physics of it too much because Holly, that's the point well, one of the points of Holly's talk. But essentially, you can see that we're not talking about squids anymore. There's no squids here. There's no low temperature. What we have are very small sensors. For reference, you see how small they are with respect to a hand. And then inside that sensor, there is a glass cell with rubidium atoms, and there's some lasers as well. And so the rubidium atoms all have a momentum, and these spins align when we have a laser going through that cell. And we can see what the intensity of that laser is in the photodetector. But when we've got a magnetic field in the brain, those spins change their orientation. And the change in the orientation also leads to a change in the intensity of the laser that is received in the photodetector. And so by looking at the intensity of the laser first that goes through the cell and what is received in the photodetector, we can infer what the magnetic field is. So more from Holly later on. So what can we do with wearable MEG? And I'll just go through very quickly about some examples, which we'll then hear more in detail later on. So pediatric MEG has been, it's a very active space. So the fact that MEG, OPMs can be flexibly put around the head and adjusted into different helmets, different head sizes. And you saw the prototype that we had back in 2021 was actually just 2 sensors on an EEG cap that nobody wanted. But there's all sorts of different types of helmets that you can think about. And this one, I believe it's a bike helmet that gets adjusted. And so that it gives a lot of flexibility. And wearable MEG has enhanced signals. So as I said before, the signal-to-noise ratio is better because the sensors are closer. But it's that much better. So 8 times better for superficial sources. These are sources in cortical sources, close to the surface of the head, of the scalp. When you go down deeper into the brain, like places like the hippocampus or the amygdala, we have about 2 to 3 times better signal-to-noise ratio relative to squids. So for comparison here, we've got a sensory evoked response recorded with OPMs, and the best squid of the setup. And you see that the difference is quite remarkable, right? So in red you see the squid, beautiful signal, but OPM is a lot. It's a lot larger signal to noise ratio, so that's great. Oops. This is a fun example. In here you see Gareth Barnes, who is the most excited person about science that you'll meet. And he likes OPMs so much and MEG so much that he actually has one OPM inside his mouth. And you can see in the picture here, he put it in there so that the sensor can be that much closer to the hippocampus. And they show that you can reconstruct sources from the hippocampus with that setup. Here's a cerebellum example from one of Sophie's papers. Beautiful reconstruction of cerebellum activity of data she collected back at UCL. More fun stuff. So as I said, these systems enable naturalistic stimuli because people can move around. They don't need to be stuck in a place, and the system accommodates noise. So if you have natural noise, natural movement, that's not a problem. That is a huge problem, of course, for fMRI, for MRI in general, but also for conventional MEG. So here we've got Elena Botto, also from the Nottingham team, playing ping pong, and beautiful signals. Oops, sorry, and then another study where the subject was dancing hokey pokey. This is a fun example from Rob Seymour, who gave a talk last year. Some of you would have attended. Actually, Matt Brooks also gave a talk last year, so some of you would have attended their talks as well. So beautiful demonstrations of that you can do. Not just do what you used to do with conventional MEG, but you can do more. And really these naturalistic paradigms are what you can do much better, or at all. Like you couldn't do this with a conventional MEG or fMRI for that matter. And then to wrap up, I'll just mention a couple of clinical applications. Of course, I mentioned the schizophrenia study that Elise and Tracy and I are conducting, but there's other things, and particularly for epilepsy, there's a lot happening in this space, mostly led by Odile Fez in Belgium. And they're doing really important work trying to develop ways to reconstruct epileptic sources of epileptic activity, which can then inform the neurosurgeon for where in the brain they might be able to resect tissue to treat a patient with epilepsy that is not treatable in any other manner. And of course, brain-computer interfaces. Sophie might talk more about this later on, but that's also another space of development. So my take-home messages. So about MEG and OPM. So both conventional and OPM-MEG measure aggregated neural activity from the scalp, magnetic activity from the scalp. They have much less spatial distortion and better source reconstruction than EEG, and much better temporal resolution than MRI. When comparing OPM-MEG with cryogenic or conventional MEG, what OPM-MEG has to offer in advance is better data quality, signal-to-noise ratio, so it's a lot better. More adaptable, more flexible, is robust to motion as compared to conventional MEG. So wearable MEG or OPM-MEG is open for business. Come and work with us. I hope this workshop is useful in informing everyone and educating everyone about the theoretical underpinnings, but also how to use it. And I hope you really you enjoy this. So thanks everyone to all the people who were involved in the first grant application, all the names that you can see here. I don't have time to go through all the names, but all the institutions, the ARC, funding body, and my team. You're awesome. So thanks very much. You can take some questions. If you can you turn on the light, Daniel? Thank you. Are there any questions? There's no questions. Oh, I don't know. That's never a good sign, Jenna.
What is OPM stands for?
Ah, very important. Of course. Optically pumped magnetometer or magnetoencephalography. Yeah. Magnetometer. Yeah. So optically pumped because you have the lasers. Yeah. Yeah. And that's how they work. And it's a magnetometer because it measures magnetic field, and then we use them for magnetoencephalography for brain measures. Thank you for that. I should have, that's where I should have started. Yes.
So what are some of the disadvantages of OPM-MEG that somebody would like to kind of start using should know?
We could probably have a session on this later on. I think from the user's perspective, one of the disadvantages is that there's not a lot of pipelines at the moment for analyzing this data. It's all very new, so a lot of the pipelines are bespoke, and Sophie is working on some of this as well. It is. I mean, it's a lot better now, but while it was being developed, the setup was quite time-consuming. It would take a lot of time. So you saw Gareth had these headcasts where you could only see the face to get people to be, very very still, and have a really precise source reconstruction that would then co-register with the MRI. And so that meant that the setup took a long time to do with those headcasts. So still in London, for example, when people book a room, they will book for a whole day. I think with our system here, it's not as difficult. The setup is come a long way. But yeah, so do you want to add any more disadvantages?
Yeah, I guess it's quite. Sorry, is that your question? So I guess it's because it's a really new field. So like one of the amazing things is that we're able to scan really young children, for example. But that's kind of quite a new field. So there's a lot to be worked out methods-wise. So it's not, you can't just kind of come straight into it and acquire data really easily without having to have to think about it. So we've got quite a few groups now working with really young children, and they have all these methods of, I think there's a lot of bribery with chocolate and stuff that comes into it, but trying to get the kids to actually sit for an experiment and not just want to take the helmet off. And there's still quite a bit of methods, I guess, to work out that when you're doing an experiment, you might be the first person that's doing it, which is really exciting and also an advantage. But you need a bit more planning with experiments, I would say.
Thank you. Yeah, I'm not sure if Sophie, do you want to add anything or?
Sorry.
No, it's okay. You can have time later. Yeah. Yep. Mr. Gan.
Yeah, fascinating stuff. So I'm wondering, especially in terms of knowledge sharing, so do you have a platform or a plan? How do you want to kind of get people to communicate, to read what has been done? I can imagine seeing that there are 7 universities. Ideally, I wouldn't necessarily need an account with University of Melbourne in order to access. So do you have plans in that space, either on GitHub, Teams, or whatever?
Yeah, I mean, definitely. So that's very much a something for us to talk about. It's we're working on these ideas, and I welcome anyone who has ideas for how to make it happen to come and talk to us. But very much so, we want to make all the code available. Could be GitHub. That's one option. But yeah, definitely there'll be a way of making this available. I also would like everyone who is going to use it to consider making the data available. I think it is really important to, in the spirit of open science framework, to make our data available. So of course it's not a condition, but it is something that is very much encouraged. And so of course ethics protocols have to be in line with that principle as well. There was also ideas about having a sort of not a mailing list, but sort of like a forum online where people can put questions and then the community can respond. So these are sort of ideas. There's already some stuff out there from the field trip guys in the Netherlands. I'm not sure if you guys have anything like this, Holly, in Nottingham, around community.
In terms of yeah, we have kind of like M&E pipelines that we've been working on. There's a field trip. I think on both M&E and the field trip website, there's now like a standard Cerca loading in Cerca OPM data pipeline that you can like copy and use. And I think trying to get things into FMB and fake bids and stuff to make it a bit easier.
So what I'm going to demo today is mainly going to be SQL based. So it has, I mean, people have done quite amazing work, so generally works quite well, but it always, most of the time, won't make best for computing sensors, because that's one of the main sensor manufacturers. So when you analyze with different kinds of sensors, sometimes you still need to deal with something which is incompatible just to go around with it. But I think as the field just is getting more and more mature, there will be more and more like broadly applicable pipeline that for you to use. And it's definitely like if you're interested in developing data analysis pipeline together with us, you're more than welcome.
Well, sure. I just realized that I didn't introduce myself. So I'm going to introduce myself. This is a bit topsy-turvy, but some of you know me and some of you don't. So I am Marta Garrido. I'm a professor here at the University of Melbourne, and I'm the director of the OPM-MEG facility. And I teach neuroscience in the mind. I run a lab that focuses on computational psychiatry and cognitive neuroscience. So this should have happened before the talk. But anyway, as I said, I've just been in Brisbane hosting an international conference, so I'm a little bit tired. So, okay, now we move on to Sophie's talk. So I will introduce her first thing. So Sophie is the facility manager of the OPM-MEG facility. She's a medical doctor by training, back when she was back in Taiwan, and then she did a PhD in biomedical engineering at Imperial College in London. Then postdocs at UCL in Birmingham, and then finally she came to the University of Nottingham. And as you saw, she's been pretty busy setting everything up, and so I'm very excited that she is going to give a talk while she's putting up the slides. How are we going? Shall I keep talking to distract them while we put the slides on?
Marta. Welcome everyone. So as Marta said that I'm still a postdoc of your group, right? And in the meantime, I'm the operator and also the managers of the new MEG facility at Uni Melbourne. So basically today I'm going to share some general group practice, I would say, like for working with OPMEG, and also give you a flavor like how we generally analyze OPMEG data. And along the course, I will also introduce a little bit of the physics and engineering aspect of the senses that's related to, well, how you can conduct OPMEG research more effectively. So, but before I start, actually, I want to emphasize, even though the physics between OPMEG and the conventional screen mag differ, but they measure exactly the same neuromagnetic fields. So the good news for you is existing MAG data analysis tools that, such as SPN, M&E Pythons, they're still valid. And most of the good practice for conventional MAG are also still valid. And because of the beautiful groundwork that has been done by many people, many researchers across the world in the past decade, we, most of the time, no longer need to be a physicist or to have a physicist on the side to run an OPMEG study. But if you can understanding the fundamental of the technologies better, it will help you to best plan your studies. And another thing is OPMEG has been developed really rapidly. So if you're new to this type of technology, it's always good to check the state of the art before you embark your studies. And a big recap about the sensors. So OPMs, optically pumped magnetometers. So the magic of the OPMs really lies with that beautiful special relationship, as Marta mentioned, between the neuromagnetic fields and the laser light intensity. And because of that, it operates at either room temperature or slightly warmer temperature, meaning that we can get rid of the cryogen that's needed in conventional MAG. So as Marta has mentioned, you get on-scaled placement, you get flexible in design your sensor array to best suit your research needs. And because the sensors are now wearable, they are also more motion robust as compared to conventional MAG. But I would say always try to think about the following before you decided to run an OPMEG study. That is to think about exactly which advantage that you want to get from your study by using OPMEG. Are you trying to study a brain area that is not very difficult or even impossible to be studied by other methods, non-invasively? Or because your participants are going to do more comfortably or they are going to do better with OPMEG, or because the paradigms that you are thinking about doing are basically not compatible with conventional MAG. Because you want to get the advantage of OPMEG, but sometimes because of that, you might need to plan your study a little bit different, depends on which advantage you want to get out of the system. So that's always one thing good to plan beforehand. Another thing is, even we have already talked about so many advantages of OPMEGs, it does come with its challenges. And the main challenges being noise rejections, well, interference suppression, and especially for generic helmet, to have good, high quality call registration is also very important if you want to know where your signals come from. So that's also the two things when we talk about good practice that we will focus on in this talk. And right, so that's go a little bit deeper in terms of the enhanced signal. So Marta has already mentioned that because we can get rid of that 2 centimeter vacuum space that is necessary for conventional MAG, so you get stronger signal, because for MAG signals, it's inversely proportional to the square of the distance between the sensor and the brain. So in modeling data, this also has been shown. We expect, for superficial sources, you get about 2 times stronger. But in practice, we're seeing around 5-fold increase in terms of the signal intensities. As you go deeper, that increase of signals, that effect gets slightly smaller. So you get around 2 to 3 times higher level of signals in deeper structures. So I want to take the cerebellum as an example. For example, if you look at the posterior cerebellum, let's look at here. So that is more close to the surface of the hair. So you get around 3 times larger signals. As you go to the anterior, which is really close to the centers of the hair, that signal increase is about 2-fold. But I also want you to bear in mind that slightly smaller increase of signal intensity actually can mean the signals from not detectable in a cryogenic system to being detectable by the OPMEG system. So just because you don't get as much as increase of signal compared to superficial source is not a reason not to run an OPMEG study. And another thing to remember is with the same decrease in distance, you are going to get larger enhancement of signals in smaller children because children's heads are just smaller. Another thing you get from on-scalp placement, on-scalp sensors is you actually get better spatial, not only stronger signal, but better spatial information. So as you can see from the figure on the left, that dipoles in the OPMEG system actually look slightly peakier, also slightly denser. And you can actually basically explain that relationship using the figure on the right, that the blue line is the on-scalp MEG signals as compared to the other 2 lines. One is the conventional MEG, the other is the EEG. So you need more components to explain the same percentage of variance. So what it means is for the same signals, on-scalp MEG provides more spatial information. And I will use one example. Suppose if you're trying to measure hand movements, using on-scalp MEG, you will have a better chance to decode the information at the resolutions of fingers or even finer than fingers as compared to using conventional MEG. So that's the special information, additional information that you're getting by putting your sensors closer to the head. And let's move on to flexible placement. So the cerebellum study that we are conducting is one of the examples. Another example here I want to show you is a study conducted by researchers at UCL. So basically what they did is to place the sensors on the around the motor cortex and along the spinal cord at the same time. So for the first time, basically you can recall movement-related brain and also spinal signal at the same time. So this basically very powerfully shows you that this flexible placement, flexible design of sensor array enable you to perform research that is not possible in the previous conventional MEG setting. And move on to, again, motion robust, just like Marta mentioned. So the fact that it is wearable and motion robust, there are 2 main advantages. One advantage is, of course, it allows you to design paradigms in a more naturalistic, more ecological ways. Like the example on the left, that you see participants either playing instruments or perform a bit of dance. And sometimes you want it to be motion robust is because either your participant is not possible to keep their head still, or in the case, for example, like epilepsy or Parkinson's disease, which Holly is going to mention to address a bit more later, is the component of the movements is actually one important behavioral data. You want to correlate, or maybe you want to understand the relationship between the MEG data and the behavior data. So having a system that is motion robust is the advantage for you. And I also want to mention, besides that, the price and the shortage of helium, one of the things is
liquid helium also takes a lot of space. So for the conventional squeeze MEG system, you need helium tank, you need dual to store the helium, well, to basically cover the sensors with the helium. So overall, in general, for conventional squeeze MEG system, you need a room sitting at around 4 by 3 by 2 meter that size, and with a portable sensor, with wearable sensors, actually you can customize design. So some researchers, like the figure in the middle, basically design the shielding environment in a way that is similar to MR tunnel style like system. And for Cerca and the Q-Spin, they now also offer this kind of small size, like lighter footprint magnetic shielded room that you can see here on the right in the slide. Again, another thing to think about is like, so with this kind of studies, some of the research questions that you want to address, some of the paradigms you want to work on might not be suitable in this environment. So it is always a way, like try to think about exactly what kind of things you want to achieve by using OPMEG, and then make a decision what kind of system you want to have with your study. All right, so we have talked about all the advantages of OPMEG. Now I'm going to talk a bit deeper in terms of the operating principles and what it gives us in terms of like how we should practice, how we should run an OPMEG study. So all right, let's go back to the figure on the left. So basically, sorry, just allow me to remind that. What do I want to talk about? Yes, right. If we look at the figure on the left, and we have already mentioned, if we place those sensors in an environment that is zero magnetic field, so basically you're going to get the laser light intensity not being absorbed 100%. You're going to get the highest laser light intensity, and that also means you get the maximum voltage output from the laser light. And when there is, so the operating principle goes like when there is a magnetic field, a tiny magnetic field that is transverse to the directions of laser line, it will cause a change of the state, and that recovery of the states would cause a decrease in terms of the light intensity that you can see using this absorption figure here. So ideally, what you want to do is you want to measure the magnetic field somewhere around here. That means you have a really sharp relationship between the change of the magnetic field and the change of the output voltage. That means even there is a tiny, like, so alterations in the magnetic field, it can be detected by the sensor. And how do we achieve that? So the way to achieve in rubidium-based sensor is basically through, one thing is densely distributed alkaline gas atoms in gas form, and also give a high temperature. So that's all pre-designed by the sensors, but there is an environment that you need to provide, at least now, for the sensor, is that environment as close to zero magnetic field as possible. Otherwise, once you go further away from those like close to zero magnetic field, you will get damping like curve, and also away from the linear relationship, which I'm going to talk about later. And in practice, say if I get a voltage output at here, the issues I will be having right now is I don't know the directions of my magnetic fields. I don't know whether if it's 20, I don't know whether it's minus 20 or plus 20. So in reality, in practice, inside the sensor, actually it also applies a small oscillating electric field to change the curve from this bell shape to this later, this kind of shape. So you will see within this deflation point, that's I can, well, in a way, nicely discriminate both the amplitude and also the directions of my magnetic field. But if you look closer, you will also notice that this line here is not purely linear. So what do I mean by not purely linear? An ideal situation is, suppose this Y is the voltage output we're observing from the sensor, and then we want a linear relationship. The BZ is the magnetic field signals that I'm interested in, and the K1 is just a constant. So this is the relationship that I want to achieve to be able to directly infer the magnetic fields from voltage output. But in reality, actually, there's this nonlinear term, and that linear term is being influenced by the magnetic fields that I'm interested in, which means can be expressed in this figure below. Is like as you go away, the magnetic fields get larger and larger. You are further away from that linear relationship because this nonlinearity term has higher impact on the Y value that you are getting. And in this figure here, I'm showing you is that the ideal linear operating dynamic range in this kind of scenario is basically quite narrow. So that means you don't want to get background magnetic field higher or lower than plus to minus 1.5 nanotesla. So even though this is quite narrow as compared to the Earth's magnetic environment, why it is still useful for neuromagnetic field is because the neuromagnetic field that we are interested in are generally 1,000 times, sometimes even smaller than this nanotesla range. So as long as you can maintain within this linear relationship situation, you're still in a quite good place. It's just on the Earth, it's not that easy to maintain that environment. So how do people, and another thing you should also remember is, in reality, actually, they are infinite series in terms of this OPM-related equation. So that also means if you have a higher level of environmental noise, that is coming from an axis which you are not interested in. If it's big enough, it would actually influence the signals that you are interested in, even though in reality, that BZ you're interested in remain constant. So that is a reason why it is so critical to have a low field environment when you run an OPM-MEG research. So how do we work around it to get a low field research environment? So the typical way doing is, of course, through OPM optimized passive shielding, magnetic shielded room using a nicely designed mu metal. So this is on the left, that is the magnetic shielded room that we have here at Uni Melbourne, and also people who are going to be part of the demo sections on the live session later are going to see. But sometimes that is still not enough. So you actually can perform active shielding. So what it means in terms of active shielding is you can use current that can counteract on the remnant field to cancel out whatever the remnant field that is still existing after you passively shielded the environment. So on top of that, this is actually how we did it when we ran the Australian prototype study in 2021. We placed basically a single triaxial OPM sensor, optimize it, and then we constantly send the reference that OPM sensor signal back through a DAC control and also a PID controller. So it automatically calculates the currents that we need to send back to 3 sets of onward coils, and then actively cancel out the field. We actually managed to cancel out the fields at least 100 times smaller than the original environmental field inside and magnetic shielded room with a cryogenic system. And across the world, there are also different researchers provide different kind of design. And on the right lower corner, so this is a design that is done by Cerca. And that's also the current design that our system is using. And beyond to make the environment outside the sensors get as quiet, as magnetically quiet as possible, another thing you can do is instead of canceling out the magnetic field outside the sensor, so people are also applying on-sensors coils. So what the coils do is to pick up the magnetic fields and then actually doing something quite similar to the PID control that we did in 2021, just except not doing it through the whole environment, but doing it through the sensors. So it pick up the signal and then calculate the feedback signal and then maintain the in-sensor environment close to 0, and using that control feedback signal as the measurements of the magnetic field in the meantime. So that is called a closed loop design. And here in this lower panel, what I want to show you is if you're using a conventional open loop system, so that's the non-linearity that I mentioned in the previous figure, you will see a drop of performance very rapidly once it reaches beyond 5 nanotesla in the environment. But for a closed loop system, you can still get really good performance even when the environmental magnetic fields goes up to 30 nanotesla, sometimes even higher. So this is the system that the 2 main players which produce rubidium-based OPMs, both field lines and Q-spin, are now using. But they are still, so far, all the OPMs we have been talking about basically are based on rubidium alkaline atoms. And there are still some limitations of this kind of sensors. One of the limitations is, generally speaking, it is sensitive up to a certain frequency, so around 150 Hertz. If you are interested in signal that is at a very high gamma band, very high frequencies, so rubidium-based OPMs will need quite some work in order to get strong enough signals. So some people actually provide an alternative is instead of using rubidium, they use helium as the magnetic sensing atoms. And one good thing about helium is it has a more stable response curve, goes up to 300 Hertz. Another thing is helium itself. So we talked about that rubidium, it needs to operate at a slightly higher temperature than the room temperature, which means even though it already gets rid of that vacuum space, you still need about 6 millimeters between the sensing part and the surface of the hair. But because the helium type of sensors, they are truly operating at a real room temperature, you can further get rid of that 6 millimeter. It's small, but get a bit more enhancement in terms of the signal strength. But in the meantime, I do want to say, at least for the current incarnations of this kind of sensors, they still have a higher noise flow compared to both cryogenic system and rubidium-based OPMs. But just want to let you know there are more than one kind of OPMs are existing in the world. And here, this is another example. They're basically using something which is slightly different physics phenomenon that the rubidium atom has, and manufacture it in a way more like gradiometers instead of magnetometers. So the very cool things that you can see is they basically did a recording in a forest, which means there is no shade environment, no shielding environment at all, and being able to recall auditory evoked fields. There are still some other things need to improve, for example, because it's gradiometer, so generally speaking, it will have higher noise level and also bigger size compared to the current versions of rubidium-based magnetometers. And also, as you can see, for now, in order to operate the sensors, you need participant head to align to Earth's magnetic field. Hence that a little bit queer positioning. But overall, this is like the beginning of an unshaded sensors telling you it is possible in the future, which is also very exciting. But all this information that I just gave you, so what does it mean in terms of data analysis? So I have told you, in terms of the good practice and also data analysis, two things we're going to focus on. One thing is about co-registration, another thing is about interference suppression. How much time do I still have? Should be okay.
15 minutes.
15 minutes, okay. Right.
20.
20, okay, yeah. So, because each sensor stands as a standalone channels, sometimes even multiple channels, if you have the sensors that can measure more than one directions of magnetic fields, and that's what we have in our lab right now, you need to design a way to place those sensors. So one way to do it, this is how this is done at the University College London. So basically, you create a customized helmet, and that inner surface of the helmet is based on the structured MRI scan. So as you can easily see, the advantage is the helmet itself is already inside the MNI space. So you can get almost perfect correlations once you put the sensors in place. And the sensor to head distance is also almost like complete optimized. But one helmet can only apply to one participant. So it has its limitation in terms of limited applicability. And also imagine if you have a series of like scans and going from one participant to another in a very short time span, then you have to just remove the sensors from one helmet and then to another. So that is time consuming. So another way people trying to do it, very much like the EEG, is using generic designs that you can design a helmet in a way accommodate different size of adult heads, different age of kids heads. So easily see that the advantage is more people can be scanned using the same helmet, but with that, co-registration quality is really critical, and I will address more in the data analysis part, in the data analysis demo. So this is also something you want to think about it. For example, if your participant is supposed to go through scans over and over again, then it might be worth thinking about using customized cast. But if your study is aiming at recruiting many people, then generic helmets might work better for you. Now we come to the thing we talked about, interference suppressions. So we have mentioned so far all the mainstream OPMs basically designed in a way that is magnetometers. So magnetometers basically just pick it up everything that is magnetic in the environment that it can pick it up. In that sense, it's just noisy. It will pick up neuromagnetic signals. That's the signals that you're interested in. But it will also pick it up non-brain biomagnetic signals, like signals from the heart, from the muscles. It will also pick it up whatever that is still existing in the environment after all those wonderful shielding that you have done. But because OPMs are not like squeeze system. So when you design an OPMs, as I mentioned previously in that unshielded example, in a gradiometers, it will come with its shortcoming, which is larger size and also higher noise flow. So nowadays, most of the practice when we run an OPMEG study, we still use magnetometers. And that's the reason why interference suppressions become so important for data analysis and also for, well, actually for the plan of your study. Again, the good news is, so you have common methods that use for interference suppressions in a lot of electrophysiological studies, such as like ICA. Commonly in conventional MEG, you use signal space separation, which is SSS, and there are other ways commonly used like temporal filtering and reference. They all in principle still work, but you just have to think about what are the specialty in OPMEG that can influence the performance of all these algorithms. For example, you need to consider whether the noise source moves relative to OPMs. One example is we commonly use ICA to reject cardiac noise. So suppose if in your case that heart noise, well, the heart is actually moved together with the hair, then when you try to use ICA, try to identify the cardiac component. That cardiac component is going to, well, looks different from the common cardiac component that you normally see in conventional MEG system. So that's something you have to model and have to think about it. Another thing to think about is the numbers of sensors. So because this field is still development, so for example, like SSS, like basically works best when there is a high dimensionality in the data, which means you need quite a certain number of channels in order to make sure, to ensure that SSS is going to work better. But a lot of times, sometimes you have maybe a couple in some researchers have a couple sensors, and in our case, sometimes we have like 50 channels. So SSS might not work the best, and you do have to take all these factors into considerations when decided which interference suppression algorithm you choose. And so far, there are also some interference suppression algorithms that are specifically tailored to deal with so OPMEG data. And our last speaker from the UK, Tierney, so they basically start with a very simple but also quite powerful way of thinking about it is just to model the external interference as a especially homogeneous field. And it turns out it actually works not bad. So here on the right, I want to show you an example is evoke response. Basically went through like simple temporal filtering. You can see some responses after time 0, but they are also quite a certain amount of noise that is like in blender with the signals. And then after the HFC perform, the signals basically get much sharper, and the signals and as compared to the baseline are also, well, cleaner, and also in the meantime now it's statistically significant, showing you like some simple models and an interference suppression algorithm can be actually be quite helpful. And another type of like interference suppression algorithm that's being developed is as the number of channels now available in OPMEGs are getting higher. So this is an attempt basically try to make some modifications on SSS in order to make it work better in an OPMEG. So beyond the dimensionality that I mentioned, another thing that SSS can sometimes causing issues in an OPMEG data analysis is because, so what SSS does is basically assuming a sphere headspace, and everything that is within that sphere headspace will be considered as coming from the brain. Everything that is outside will be considered coming from the environment and then being rejected. So one thing is that assumption, saying the headspace is sphere, is actually not true. For most of the people, the brain is actually slightly elongated. But because in conventional MEG system, there is a certain amount of distance between the senses and the brain, so that imprecise assumption is not such a big issue. But it becomes quite a big issue when you pull all the sensors really close to the surface of the brain. So what this so a variation of the SSS does, one thing it does is instead of assuming the brain to be perfectly sphere, a perfect sphere, it basically assumes the brain to be spheroid instead of a perfect sphere. Another thing it does is also it tries to orthogonal project the signal versus a noise. The very simple way to say it is just it only removes noise that is completely uncorrelated to the signal. So it will not increase the level of noise as it applied the algorithm. So maybe Tim will talk a little bit more about that. Here just an example try to show you in a very simple example using visual stimulations. So what you normally see in this kind of paradigm is there will be a 4 Hz oscillatory wave in the posterior part, the visual part of the brain. And on the left, this is the signal only went through simple temporal filtering. Not too bad, but there are still a certain amount of noise. And then in the middle, basically, this is the data being presented after data being applied with SSS. So you can see instead of increased signal to noise ratio, it actually introduced noise, and the signal now becomes even harder to be seen. And on the right, this is an example applying these different versions, adaptive multipole models, different versions of SSS, and now you can see that the 4 Hz oscillatory waves become very clear and also stronger. And here is someone who just asked, but I'm not going to go into detail, is, so with the strength of being able to conduct more studies with, MEG studies with some movement, one thing you of course have to consider is movement artifacts. So there will still be movement artifacts is because as you move the sensors along, the background field and also the orientations of the background field will change with the movement of the sensors. But it is still doable. And also, all the principles that I talked about, which are good practice in stationary OPMEG recordings, are still all applicable to OPMEG studies with movement. So low field environment, closed loop design, and good interference, so suppression algorithm, they are all still important. And another thing we really strongly recommend you to do is it will work much better if you're studying with a movement to have motion capture data together, and later that you can apply the motion capture data to linearly regress out the movement-related artifacts. So maybe Holly is going to talk about that. But if not, yeah, if you're interested, there are some examples online, and if you're interested in running such kind of study, we are also very happy to work together with you. So the interesting conclusion is, well, basically OPMEG offers, we talk about our enhanced signal qualities, flexible sensor placement, improved robustness to participants' motion, but there are key challenges like this restricted sensor dynamic range, like the nonlinear responses, like the need for effective interference rejection, but significant progress has been made both in the hardware and the software sides, advancing the feasibility and the reliability for OPMEG. And currently, there are still some limitations, like here I just mentioned two. One is the relatively narrow bandwidth, and there are people working on this field, try to design either make the bandwidth to be higher in rubidium-based OPN or using a different regime-based OPNs. And there's still need for strict magnetic shielding, at least for now. So that's the end in terms of the group practice. And then I will use the time that I still have just to walk you very briefly. It's an OPMEG data analysis demo. And the data I'm going to use came from single participant and recorded by Elise, Tracy, and me. And so the paradigm is basically a 500 Hertz and 10 millisecond pure tone auditory stimulation with 800 repeats. And we recorded it using 50 field line OPN sensors. It's operating at a single axial mode. And we place the sensors like bilateral frontal temporal. And the main thing I want to show you is we can, starting from this kind of wiggly lines, to something like a typical M100 auditory evoked field. So the first thing is, at least at this moment, so when you have an OPN data, you need something, some way to integrate them and then import the data. What do I mean by integrate them? So the OPMEG data has not only the magnetic fields data, that's the MEG data itself. It also has important metadata. I'm losing my sound as I go along. So that's about like the name of the sensors, the type of sensor. For example, here you can see it's magnetometer, the units that you're recording, the sampling frequency. And very importantly, it's also, you will need information about where your sensors are, regardless which kind of coordinate system that you are using. And if you want to basically run source recovery later, you will also need structured MRI. And the SPN OPM create function is a function that helps you basically to integrate all these different kinds of information that are important for data analysis, and then to create an SPN tool or a MATLAB compatible file for you to run the analysis down the road. And if you are using generic helmet, as we are doing, when you are creating this file, it's very important to put the helmet coordinates and the structure MRI coordinate in the same space. And the way how you do it is basically you will need something either an optical or the Pohemus scan. And that scan will need the information from important landmarks both on the helmet and also on the head. So that's the head fiducials and the surface of the head. And that scan will help you basically to align the helmet coordinates and its landmarks to the surface of the structure MRI. And at the moment, if you're using optical scan, so you can use SPN, a function in the SPN called SPN OPN OPREG to do this. If you're using Pohemus scan, that's what we are doing right now, you can combine the field trip toolbox, which is one function called FT elect align and FT mesh align, to help you to run this and then to get the correlation done. So once it's done, it's basically moving that helmet coordinates onto the MNI space, and then you will get this nice figure that the surface are now sitting nicely on the surface of the hair or nicely on the brain mesh. So once that is done, that's like you get the data prepared, and you can first look at the data. So you can use SPN EEG review function to look at this raw data in time space. The x-axis is the time, and the y-axis is the magnetic fields, and different lines means different sensors. 5 minutes, okay. Yeah, so basically, what you can see, at least for me, is there are a lot of slow drift of the signals. Not that many useful information. So specifically for OPM1, is there one function that is very useful, very helpful, is to look at the power spectrum density. Instead of look at the signal in frequency space, you look at the signals. Well, instead of look at in time space, you look at in frequency space. So here you can see I have quite some slow noise, and that's probably more like motion related, which OPM itself is highly influenced by that. And I also have a peak at 50 Hertz, so that is, and also 100 Hertz harmonic. So that is the power line load noise. And in our environment, we also have quite prominent 30 Hertz. Sometimes it's there, sometimes it's not. And so the usefulness of this PSD is actually help you to know later down when you filter your data to guide you how you should design your filter. Another thing which is also very helpful is in an ideal world, you want all your sensors to work in an optimal state, but it's not always the case. For example, here, I can see my sensor 11. Somehow, it's just much more noisier across all the frequency space. So I can now label my sensor 11 as a bad channel, remove that from my further analysis. So that's another way to use the PSD. Once that is done, so the nowadays OPM-MEG system basically has a relatively, well, high sensor like sampling rate. It's always sampling at a above 1,000 Hertz frequency sampling rate. So if the signals that you're interested in is basically well below the sampling rates of the OPMEG system, for example, like here, we are the sampling rate that we had during the time of the recording was 5,000. Normally, we will do a downsample. The reason we do a downsample is actually, so that raw data you show, it's 50 channel. It has some other components, so it's about 20 minutes of recording. The size of the data is about 1.5 gigabytes. So it takes quite some storage space, memory space, and also when you run data analysis on the data with this size, it also takes quite a few computational powers to run it. So if the signals you are interested, you're quite certain you don't need thousands Hertz sampling rate. One optional we actually quite commonly do is to downsample it. Like here, we basically downsample from, just use SPN-EEG downsample function to downsample it from 5,000 to 200 Hertz. And then what we did here, this PSD which I show here is just basically going through first the bandpass, and based on the signal that I'm interested in, run a bandpass filter. And then because when I look at the PSD, still significant 50 Hertz peaks, then I ran an additional bandstop filters to further remove that line noise. And sometimes if that 30 Hertz is not what you are interested in and still there, you can run additional. So it is, they are optional, and also depends on the signals, quality of the signals you have, and also the signal that you're interested in. And in the case that we just mentioned, sometimes the signal you're interested in and the noise are actually sitting at the same frequency, then simple temporal filters might not work best for you. And the good thing is that using SPN to analyze the data is because both of the interference suppression algorithm that I talked about actually has well-written existing functions in the SPN toolbox. So you can, if it's needed, you can either run SPN OPN HFC, so that's homogeneous field cancellation, or adaptive multiple models, that's the AMM, to perform interference suppression. And here, we actually didn't need to do that. And once that is done, so the rest of analysis is actually pretty much similar to all the MEG and EEG analysis that you did. You simply just epoch your data. Here we epoch minus 100 milliseconds before the onset of the auditory stimulation to 250 milliseconds after the auditory stimulation. And then we just run, use the minus 100 to 0 millisecond, that 100 millisecond window as baseline to run baseline correction, and then average the data, and then voila, you got your N100 auditory evo fields. And I also use a little bit of customize to draw a not so beautiful top plot to show you at that peak around 100 milliseconds, the field map. So that's basically what you need to do to reach this stage to get a good sensor level evo response. And I'm going to stop here. And so from this onward, if you're interested in running source localization, of course, all the tools of source localization like beamformers, like dipole fitting, or like minimum nodes, all kinds of tools that you can use. And you just do it as how you do it for conventional MEG data. So, conclusions. OPMEGs offer advantages, and we have mentioned it again and again: strong signals, good quality of signal, flexible sensor placements, natural possibility for naturalistic or flexible product design, and also being able to accommodate study population that might not be able to receive a neuroimaging investigations or MEG study otherwise, and developers in hardwares like active shielding, closed-loop design, and software like interference suppression and algorithms allow OPMEG to fulfill its potential. It is developing very rapidly, so join us in the exciting field. And with that, I want to say thank you, and I will see you later in the lab if you are joining us for a live lecture.
This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Welcome back, everyone. So I hope you all had lots of fun with the hands-on sessions in your groups. And now we're back for a couple more talks before we go into the reception. There'll be nice drinks, and some people outside. So two more talks, and then we're all done. We can celebrate. So the next speaker is Holly Schofield. She is a physicist working on the development and application of human brain imaging, specifically the conception, design, implementation, and validation of novel hardware with an emphasis on building high-density neuroimaging arrays using quantum-enabled magnetic field sensors. That is exactly why we invited her. She has a dual role, both as a scientist, as a scientific researcher in the Sir Peter Mansfield Imaging Centre at the University of Nottingham in the UK, and also a product developer at Cerca Magnetics, which is the company that built the magnetic shielding room that you all have seen. So she was here last year, that's when we met, and we loved her, and we said, please come back, and she did. And of course, Cerca does not only the rooms, but also does the full package solution of putting in the sensors and the room together. So I think I'll let you talk now. So she'll be talking about applications, the backpack, and it's going to be amazing. So thanks, Holly.
Hi everyone. Firstly, thank you to Marta and Sophie and Sarah for having me here today. I'm really excited to talk to you, and it's really exciting that OPM-MEG is in Australia. And so yeah, my talk, I've titled it OPM-MEG The Next Generation, which I realise sounds a bit Star Trek, but I'm really just going to kind of take you through some of the history of the development of OPM-MEG at Nottingham, which Marta touched on a little bit this morning, and kind of talk to you about some of the latest developments in the technology and kind of where we see it going next, and just generally get you excited about OPM-MEG, as excited as we are. And so yeah, just a quick overview of the talk. I'm going to talk about what OPMs, optical pumped magnetometers, are. So Sophie and Marta kind of laid the groundwork very well for this, which makes my job easier and hopefully makes it all more understandable. So I'm going to talk a bit about the physics, but I won't, I'll keep it light on equations and things because I appreciate we've all just had afternoon tea and I don't want to put you all to sleep. And then talk about, some of the history of the OPM-MEG development, so some of the early work that was done from around 2015 to 2019. So we've been working on this for around 10 years in Nottingham. And then take you through some of the kind of exciting latest developments, like I said, and talk about what's next for OPM-MEG. So optically pumped magnetometers are quantum sensors that allow us to measure magnetic fields with light. And so they're a fairly new kind of quantum magnetometer, although development actually first started in around the 1960s. But what they have seen is really rapid development in the sort of last 10 years or so, in terms of actually making them more useful for outside of sort of bench-top engineering spaces. So one of the things that's really contributed to this is the commercialisation of OPMs by companies like Q-Spin, Fieldline, Mag for Health. It's really kind of pushed the development of them to go from these kind of large, complex systems that wouldn't be very useful on a brain to kind of practical sensors that are really useful for neuroimaging. And so how do they work? So we've kind of had bits and bobs and overviews of this, so hopefully it will make nice sense. So inside of our OPM, we have a laser, a glass cell filled with rubidium atoms, and a photodetector. And we use rubidium because it's an alkali metal, and it has a single outer electron which is easily manipulated. And this outer electron has a property called spin, which is related to its magnetic moment. And when we apply no laser light to this and we have no fields, our spins are kind of oriented randomly. So we have no net magnetization in the sample. We're not magnetically sensitive. So then what we can do is apply circularly polarized laser light, which transfers both energy and angular momentum to the electrons, and it essentially prepares them in this it puts them all into the same quantum state, where the spins are actually aligned in the direction of the laser beam. And we call this the dark state because when we apply this laser light and transfer the angular momentum, we eventually get to a point where the spins, where the electrons can no longer absorb any energy and no more angular momentum. And so the laser light actually just passes straight through the sample. And so the sample is essentially transparent to the laser light. And at this point, we get a kind of maximum reading on the photodetector. So it's maximum voltage. And in this state, the sample is very, very sensitive to changes in magnetic field. So any external magnetic field that we apply has a very strong influence on the bulk magnetization of the sample. And what this does is it pushes the spins out of that alignment and it changes their quantum state so that they're able to absorb energy and angular momentum again. They're no longer in that dark state. But what this means is that they begin to absorb that laser light again, and the light that we measure at the photodetector goes down. And so we can use this to infer the magnetic field that we measure. And so to actually kind of make this work in principle, we have to apply a sinusoidal modulation field, which is something that Sophie touched on. And that essentially gives us directional sensitivity and allows us to make that, that transfer of voltage to magnetic field. And so the response that we see at the photodetector, this is one of my very few equations, I promise, is approximately given by this equation here. And so we can see that if we imagine we have very, very small bx here, so in the case, we have very, very small bx, essentially this equation kind of collapses down and we get what is a linear relationship. So Sophie touched on this earlier as well. And so what that means is that OPMs are zero field magnetometers, because we can measure very well the relation between the voltage at the photodetector and the field at very, very low field measurements. And yes, so this allows us to convert that voltage at the photodetector into field. And this is something that we refer to as the gain of the OPM. And so you've had a few explanations of this now. Hopefully it makes good sense to you. But if you're still confused at all, then you can find me at the drinks session, where maybe we can do a practical demonstration using a beer bottle, which I think Marta found particularly effective. And so I'm going to talk about how we actually sort of started applying these principles to brain imaging. And so the vision in 2015 from the group at Nottingham and the group at UCL was, so they'd been working for a long time in squid MEG, and this is kind of what those systems looked like. We've seen those from Marta and Sophie. And for all of the reasons that they discussed, you know, the fact that these are kind of one-size-fits-all systems, we have that large sensor-to-scalp distance. They envisaged this system with OPMs where we'd be able to bring the sensors closer to the scalp, we'd be able to get rid of that big cumbersome system, and they would the systems would become wearable. So instead of just having these sort of static measurements, we would start to be able to move around. And this work kind of started with some simulations back in 2016. So this was work done by Elena Botta, the CTO of Cerca, and also one of the postdocs at the University of Nottingham. And she was looking at, this is a favourite figure, I think, because we've all used it, but it really does highlight very nicely why we want to use OPMs. And so we know just by bringing the sensors closer to the scalp, so the magnetic fields that we measure from the brain drop off with an inverse square law. So simply by bringing the sensors closer, we can increase the sensitivity that we have to those fields. And then this was a little bit more of the simulation work. So as Sophie and Marta mentioned, in the simulations we were seeing that we could, you know, really push this to see up to 8 times the SNR in some cortical regions. And that brought us to the first channel recording, so one of the first OPMs that the group had. And this always makes me laugh, this photo of Gareth. I think he was like bolted into this I've heard lots of stories about it. And how he had a straw where he was like sipping to try and get water from the side. And it was really exciting because we were able to see in that experiment that from that OPM, the response to a median nerve stimulation was 4 times higher. The signal that we measured was 4 times higher in an OPM than it was in the best squid that we were able to measure that response in. And so that was really promising. So it brought the team to want to really create, you know, an array of these and get these into a neuroimaging system. So that kind of brought us to the first wearable OPM array, where we had a few of the Q-spin Gen 1 sensors. So these were, you know, kind of about that big. They were originally designed to be benchtop and held by an engineer for various other applications outside brain imaging. And they were mounted into this kind of bespoke helmet that allowed for, like Sophie was saying, very accurate co-registration and made the system wearable. And the first experiment that the team did with this was to really utilise that additional head movement that you could now get versus in the SquidMEG system. So Elena did an experiment where she was bouncing a ping pong ball for 10 seconds and then she had 10 seconds of rest, and she repeated this 29 times. And what we were able to see is that despite this kind of naturalistic head movement that would be way outside of that 5 millimeters that you're limited to in SquidMEG, we were able to see the expected brain response, which is this modulation of the beta oscillations in the motor cortex, where you get this desynchronization and rebound. We were able to see that response very, very clearly, despite this additional kind of head movement. There's a little video demonstration for doing it. this is what impresses me the most, more than any of the, you know, incredible brain imaging, is that she managed to do this 29 times without dropping the ball. I personally think that's why it got published in Nature. Yeah, and so then one of the main benefits that has been kind of talked about so far is that with a wearable system, it's more child-friendly. So we know that children can't sit still for very long, and they also have small heads. So putting them inside these large dewars doesn't really work, and we need kind of an additional system for it. So one of the problems with, I guess, these initial setups is that they don't look very child-friendly. So you definitely don't want to be bolting a child into a bespoke cast. And there was actually a low-budget Spanish horror film that took this exact design of a leather helmet and turned it into a torture device. So at that point, we knew that we needed to do a little bit of redesign to make this more friendly. And so that's what the team did. So this was work from Ryan Hill, and they essentially took a bike helmet and drilled holes into it so that they could put those Gen 1 OPMs into it. And it was significantly more child-friendly. It was very well tolerated by the children, and yeah, it was kind of colourful and nice, and they were able to be scanned in it. And so this initial paradigm was actually a mother stroking the child's hand, which caused this lovely kind of somatosensory response. And then a kind of an exciting other application of this work in conjunction with UCL and by Jill Roberts at the University of Nottingham was to actually use VR simultaneously with these recordings. So in this paradigm, the participant was had a wall in front of them in the VR, and there was a checkerboard pattern behind them, and they were instructed to either lean to the left or lean to the right around the wall, so that they would be exposed to the checkerboard pattern. And we were able to see that you could localize that visual activity to either the left or right hemisphere, dependent on whether the person was leaning left or right around the wall. And so there are some challenges with this in that most VR headsets are very magnetic, you can imagine, so there was lots of removing screws and all that kind of stuff, but it was really exciting to see that demonstrated. And so then we got the first Gen 2 OPMs in 2019, so that was a real big step in terms of the miniaturization of these sensors. So like I said, the first Gen 1s were kind of designed to be handheld on a desk, so the Gen 2s, they really focused on making them as small as they could, so we can fit more around the head, they're more lightweight, and it makes them significantly more wearable than these larger sensors. And so they're about the size of a pound coin or a Lego brick. We did have a reviewer once say, well, what size Lego brick? Which was a little bit picky. So then, yeah, in 2019, we started to also do some simultaneous OPM-EEG measurements, which is something that's been really, there's been a lot of interest from people in the field on that. Because for the clinical pipeline in the US, for things like epilepsy, you need to have EEG, and people kind of used to looking at EEG signals too. So it's nice to be able to do the two measurements simultaneously and then not interact with each other or cause interference. And so then by kind of the end of 2019, we had 50 of these single axis Gen 2 OPMs, which gave us a 50 channel system. And yeah, you can see there was kind of quite a lot of development here to get to this point where you had something quite nice, quite wearable, and was given as, you know, mostly whole head coverage. And so what have we done since then? What are kind of the exciting developments that we've done? So one of the things that we wanted to really focus on was, well, we have, you know, this array now. What can we do to make the most of it? How can we exploit it as much as possible? And so that's what I'm going to take you through first. So one of the kind of big steps to our improved array design was the introduction of triaxial OPMs. And so in a triaxial OPM, where we apply that modulation field and get a measurement along the axis of the modulation field, in a triaxial OPM, if we apply two orthogonal beams, so we have the same situation that we had before in those first slides, but we're now using two separate laser beams. If we actually apply our modulation fields in both X, Y, and Z, then you can actually get two orthogonal measurements from each laser beam. So you can get two measurements per laser beam, dependent on the direction that you put the modulation fields in. So you can't measure along the field, you can't measure along the direction of the laser beam, but you can get the ones orthogonal to it. So if beam 1 is oriented in Y, then it would be sensitive to external fields in X and Z. And if beam 2 is oriented in X, then it would be sensitive to fields Y and Z. And so this actually allows us to make a full characterized measurement of the field in all three directions. So why do we need these sensors, or what's the benefit of these sensors? And so one of the real benefits is that if we look at infant brains, for example, we get very, very close to the brain, because in infants we have a much smaller distance between the scalp and the brain. And so we're already bringing those sensors closer to the scalp than we are in squids. And so our fields become much more focal. They're higher in amplitude, they're much more focal fields. And so if we only measure in the radial axis, then we can miss or underrepresent some of the information, just because the fields are so much more focal. And what we can actually see is that when we add in the triaxial sensors instead, we manage to make a much kind of, we get more homogeneous coverage over the brain, because we're not missing as much information, essentially. And so with these kind of arrays where we bring the sensors really close to the scalp, it's really important for us to get this full characterization. And another kind of benefit of the triaxials was interference rejection. Bless you. So I won't talk too much about this, because this is something that Tim will cover in his talk. But essentially, when we use, so if we look at external interference, something that Sophie had mentioned is that these external interference fields, essentially, if you think about a field that's a long way away, then by the time it decays and it gets to the helmet, it looks fairly uniform across the sensors. And so when we have just radial measurements only, the kind of these uniform interference fields and the fields that we measure from the brain can look quite similar. It's harder to differentiate between the two. And using triaxials, we're actually able to fully characterize that, so we can see the difference between them a bit more. And so this was data that was recorded in a handwriting task. So the participant was writing down words that were shown to them on the screen and then lifting their head back up. And we have this kind of 16 hertz artifact in Nottingham. Loads of people in Europe have this artifact, and we're not 100% sure what it is. We think it might be trams or trains or something. And so we can see that just taking the radial component of our sensors, when we actually reconstruct this and try and look at the data, you can see this 16 hertz line within the TFS. But when we use all three of our axes in our reconstruction, we're able to kind of get rid of that when we do our source reconstruction. It kind of falls out, because we're able to better differentiate between interference and brain signals in our data. So then, yeah, I guess one of the questions, and this was a question that was posed to me in the break as well, is, well, how many sensors do we need? And so when we did these initial simulations, or when Elena did these initial simulations, she was simulating fields from 275 channel squid and 275 channel OPM systems. And that was kind of what was giving us these amazing theoretical increases in SNR. But there are a few things to actually consider when we put this in. As always, when you take things from simulation to experiment, there are things to consider. So the OPM noise floor is slightly higher than the squids. So in dual axis and single axis sensors, we look at around 10 femtotesla per root hertz or slightly less. The triaxial sensors, the trade-off that you split that beam is that you just get inherently slightly lower sensitivity. So that raises your noise floor to about 15 femtotesla per root hertz. in a squid, you're looking at 5 or less. So the OPMs have a slightly higher noise floor. And most OPM systems have fewer measurement channels than conventional MEG systems at the minute. So like I think probably the most that people have in OPM systems at the minute is around 200 channels of measurement, which then kind of inherently means that you're measuring less field with your array. And as has been covered in the other previous talks, OPMs are formed as magnetometers, whereas squids are gradiometers. So you're more susceptible to these interference fields. And so what that meant was that when we were doing lots of kind of comparison studies with whole head OPMs and again squids, that we were coming out like a little bit better in SNR, but not to the extent of what we were seeing in our simulations and what we knew we could really push the OPMs to achieve. And so we wanted to ask, how could we improve the sensitivity of our system? And so this is my only other equation, I promise. So we've talked a lot about source reconstruction in the previous talks, and so when we actually want to estimate what the source is in the brain from what we measure in the sensors, we have our reconstructed amplitude that we're assuming it is, which is just equal to the source amplitude plus some error that comes from our beamformer. And this is a horrible equation, but it drops out if you do some derivation very, very nicely into this really intuitive equation where basically the error on your reconstruction is just equal to the standard deviation of the sensor noise divided by the Frobenius norm of the forward field. And what we mean by this is basically just the total field that you measure in your array. And so to improve our SNR, to reduce the error on our reconstruction, we can either reduce our sensor noise, or, which sounds very, very obvious, how do you get better SNR? You reduce your noise, but it's actually a very difficult thing to do in terms of sensor design to get that noise further down. And so one thing that we can focus on is improving the amount of field that we measure, and we can do that in two ways. So if we imagine a source at the back of the head, it's like in the visual cortex, which is shown here. We can increase the amount of field that we measure by either just increasing the number of sensors, so by pushing these sensors closer to the number that we have in squid systems, or we can redistribute our sensors. So one of the real benefits of OPMs that's been talked about is our ability to be able to flexibly place them wherever we want to. And so by using kind of clever array design over the areas that we're interested in, we can increase the amount of field that we measure and push that SNR up. And we only had a limited number of sensors when we started looking at this, so we decided to choose to redistribute our sensors and see where that would get us. And so we started with looking at kind of a low amplitude brain response where we would really see the benefits of this increased SNR. And so we were looking at natural viewing. So just people, this was a task where you were shown a 5-second clip of somebody walking around Brighton, and then you had a bit of which is a seaside town in the UK, and then you had a 5-second break. And this is known to induce these kind of broadband gamma responses that are very low in amplitude. And so what we did was we took a bespoke 3D printed helmet that was significantly less bolted in than ones we'd worked with previously, and just pack as many sensors as we physically could over the visual cortex. And so what we were able to see is that we got this really, really nice broadband gamma response. And actually what we could do to kind of look at the benefit of this is actually artificially change that channel density. So we can just turn sensors off in our analysis, right? So we have, in this system, we had 64 sensors, all with triaxial measurements. That gives us 192 channels of measurement of the field in total. And so we can kind of artificially turn those channels off and redo the reconstruction and see what kind of SNR we would be getting. And so what we can actually see is when we do this, we get this beautiful linear response that goes up with channel density, which agrees with our kind of our nice error equation that we got out of the last slide. And what we could actually see is when we repeated this in squids, we were able to surpass the SNR significantly surpassed the SNR that we were able to see with this response in the SQUID system. So that was really exciting, but I guess it's not always the whole picture, right? So there are plenty of experiments where you might want to look at the whole brain, or you don't really know exactly where you're looking. So although we can get this really nice improvement in SNR with judicious sensor placement, we also wanted to look at what would happen if we increased the number of sensors in our system as well. And so that kind of brings me on to this improved control hardware. So when I joined in my PhD in 2022, this is kind of what the control electronics of our system looked like. So every single sensor, so we had 64 triaxial sensors, and every single one had a control unit kind of about this big, and they were housed in this large rack. And every single sensor had an 18-foot cable that came from the electronics into the MSR and connected to the sensor head. And this was great. It gave us this flexible wearable array. We managed to get quite a lot of really great data with this system. But like I said, we have this large electronics rack that was quite complex, and this heavy cabling. So the cabling itself was about 14 kilograms, which we're able to kind of mitigate that, but it's still quite a lot for somebody to be able to wear. And so because of these two kind of challenges with the system, it was difficult for us to increase the channel count because of how big the electronics was, how complex it was, and it was also difficult for us to have that true free movement, because you can imagine when you're not sat down, you have to support the weight of all of these cables. And so there's a conference in OPM, it's called WOPM, and in 2022, QSpin presented this idea of a backpack electronics. So that would bring everything from that big, large electronics rack down into something about the size of a backpack. And we were lucky enough to get one of the first ones of these systems in Nottingham in 2024. And so this is kind of what it looks like. So the real benefits of this, obviously, are the miniaturized electronics, so you no longer have this big cumbersome rack. You massively reduce the amount of cable weight, so there's only really one, there's an Ethernet cable and a power cable that come out of this backpack. The backpack itself weighs about 1 kilogram-ish, so not very heavy. And in theory, this system should be able to support an arbitrarily large array, so it was designed with the idea that you would be able to connect multiple of these backpack electronics together and synchronize them so that you could just keep adding channels in a much easier way than it would have been before. And one of the benefits of this as well was that it came with full triaxial closed loop mode, so that was something that Sophie covered in her talk, about it giving us this kind of increased dynamic range of the sensor. And so we had to make sure it worked first. So the first thing that we did was a comparison study. So this was composed of 3 stimuli. So we had a button press to give our kind of standard beta desynchronization and rebound that we see in MEG. We had some kind of centrally presented circular gratings, which give us this nice gamma response, visual gamma, that we expect to see. And then also some kind of emotional faces, which trigger this evoked response in the fusiform gyrus. And so we repeated these experiments in 2 participants 6 times in each modality, and we did it over the course of we also did it in the squids as well, and so we did like 36 scans in 3 days or something, and I was losing my mind. But we did find a correlation of greater than 90% for all the responses between the 2 systems. So we were able to kind of, with confidence, say that we were measuring the fields that we thought we were measuring, and that our new electronics was doing what it should be. And so we'd done the sensible thing, and we'd made sure that it was working. And so the next thing that we wanted to do something that you could never have done with the old control electronics. So we packed it into a suitcase and we took it on the train all the way to Brussels to our collaborators in Belgium. And so this is my supervisor Matt carrying not only all of the electronics but also my bag. And when we got there, it took us about 30 minutes to set up. So we literally just took it out of the suitcase and plugged it in. Obviously, they have they have an MSR on the other end, so we were able to unpack it, set it up in their shielded room, and we were scanning 2 different groups of healthy volunteers. So we scanned 5 people in Brussels and 5 different people in Nottingham, and we were able to show a 96% correlation between the responses measured in the 2 sites. So we were able to show that you can kind of pack this system up, take it to another lab, and you can get very, very similar cross-site measurements, even with a different room and a different setup. We also scanned 5 paediatric epilepsy patients, but that data is still being processed. And so, yeah, so this was, really exciting to see this new electronics. And once we kind of done lots of testing and scanning with our 64 sensors in this one backpack, we then wanted to try and push that high density OPM-MEG and increase the number of sensors in our system. And so we had 128 triaxial Q-spin OPMs here, which gave us 3 independent components of field measurements. So that's up to 384 channels. So now actually far surpassing the number of channels that we get in SQUID. So SQUID systems you typically have up to around 300. And we did this by connecting them all to 2 of those Neuro 1 electronics backpacks. And we had to synchronize the 2 systems so that they were running on the same clock using an external signal generator. But the kind of whole system in total looked a little bit like this. And in practice, it looked a little something like this. So you can see the 2 backpacks connected up together at the back there. And yeah, so we had kind of notionally a 384 channel system, which was really exciting to see because it was kind of, the first time we had more channels than a SQUID system. And so the data that we have from this system is very, very preliminary, but something that was kind of a fun thing that I wanted to show you that I think kind of showcases that benefit of having whole head high density coverage is this kind of resting state data that we did. So we had a single participant watch a film from a very, very old Al Pacino film called Dog Day Afternoon, and this anonymous participant had to watch a 10-minute clip of this film, the same 10-minute clip of this film, 5 times in a row, and could probably now quote you it back, like word for word. So we have this kind of whole head high density coverage, and we were looking at, because we're looking at resting state, we're looking at kind of whole brain. And what we actually wanted to do was look at signal leakage that we measure between different regions in the brain when we do our source reconstruction. So you can think of this almost as like a measure of spatial resolution, because if you're reconstructing signals in different regions of the brain, if there's kind of leakage across those brain regions, you're seeing correlation between what you measure. Then the amount you can minimize that, you're getting kind of better spatial resolution measurements, because you're not seeing leakage between the regions. And so what this plot here shows is basically doing a similar thing that we did with our turning the channels off and on in our broadband gamma experiment to simulate what it would look like with less channels. And we looked at what it would be with 192 channels, so 64 sensors evenly spread, versus our kind of, we had around 350 in total in the end, good channels in our array. And we could see that what we were getting is basically a reduction in the leakage between our regions. So you can see here, this kind of shows that we get this reduction because all these numbers are positive. So we're taking a difference between our small array and our large array, so we get this positive difference, which means that we're basically reducing the leakage across all of these regions. And we could do this basically if we went from our 192 channel array to our 350 channel array, we would get an increase of leakage of about 30% by reducing the number of channels that we had. And so we kind of addressed one of our main limitations with being able to increase the number of channels in the system, and then we wanted to kind of look at free movement. So Sophie has kind of touched on the free movement element of this of the system already a little bit, so I'm going to kind of cover some of the key things that you need to know when you start doing a free movement experiment in OPM-MEG. And so we have these wearable systems, but can we actually move freely? So this is, again, something that Sophie and Marta have covered a little bit. So what we actually see is that because we are able to bring that field down in the magnetically shielded room to around a few nanotesla, but to an OPM, that's still quite a large field. So when we move the head, like we can see in this nice plot, we actually create large changes in field that happen with it. We get these movement artifacts. And so the closed loop operation that Sophie has talked us through actually helps the sensors to stay in range, but we still measure these movement artifacts, right? So we still have to pick out the brain response from these movement artifacts. And so one way that we can deal with that is by using these compensation coils in the MSR. And so, you know, the ideal situation is that we can remove the background field completely, so we get no movement artifacts, but actually in reality that's very hard to do, but we can reduce it using these compensation coils. And so in this data here by Molly Ray, we can see that by using, so this was basically a grating that flashed at 6 Hertz to give a visual stimulus. So we expect in our kind of PSD, we expect to see a change in field that correlates with that 6 Hertz grating. And so what she did was have the participant look at this grating but move their head, make kind of natural movements. And she did this with the background field of 1.5 nanotesla, which is around what our field is when we just have the shielded room and no nulling, no field control whatsoever. And it's kind of hard, you can see it's very hard to sort of pick out that 6 Hertz response, so it's not as clear when you have this kind of, when you have this movement there and you have the field. With the field control, we can see that you're able to actually pick out that 6 Hertz response much nicer. So you're able to, basically, you're not masking your signal as much with that movement artifact. And so, yeah, the kind of latest developments in this have been this kind of matrix coil system from Niall Holmes. So it's essentially reconfigurable coil technology. So we have multiple independently controlled coils, which allows basically us to create a volume in the MSR and control that volume so that we null the field to as low as possible. And we're actually able to get down to sub-nanotesla levels when we use this active shielding. And so this allows us to do some kind of even more exciting movement studies. So you can see in this example here, so we have Elena and Matt. So with one of the benefits of this kind of reconfigurable coil technology is that you can also create multiple volumes. So here there was 2 volumes created so that 2 people could be scanned at once, and they were able to ping pong back and forth, which I think is also still very impressive because I would definitely drop the ball. And then we have this example from Niall where he was actually moving around and moving the null volume so that he was able to continue pressing a button. And actually you can see that you can continue to measure that beta desynchronization and rebound that you expect from the button press. And I always make the joke that that isn't even sped up, he's just moving at that speed, but he's just that excited about coils. But yeah, so then you can see very nicely that we're able to measure the motor response in 2 participants simultaneously while they do that task back and forth. And so I can see that I'm going quite on time, so I'll kind of hurry up. So one of the nice examples of this free movement with the backpack, so all of that movement that you saw was using the kind of heavy cabling, and so it's fine when we do it in healthy participants, but when we want to do that in patients, it's much harder to translate that, right, because they just can't carry it. So that was really where this backpack electronics came into as benefit. So we had this study with 20 patients with MS and 20 healthy controls, and we were able to actually look at the response from a finger abduction, so this beta desynchronization response, when the person was seated and when they were standing. And we can see this significant difference between our patients and our healthy controls in our actual rebound, in our beta rebound. So we can see this significant kind of decrease in it. And this is something that was seen in previous literature when the person was seated, but we're now able to measure this in kind of different scenarios where they're standing. And this is kind of some really new results that I find particularly exciting. So this was using Parkinson's patients. So Parkinson's patients have an issue where when they try and move or turn, they can experience freezing of gait. So they become kind of, they become so they can't move. And so we have this experiment where the person wears the system while they turn. And we'd measured this now in 8 Parkinson's patients and 7 healthy controls. And this is, again, kind of similar kind of work that's been done seated. So people have done looking at that beta desynchronization in Parkinson's patients while they're seated. But we're now able to do it in this kind of moving paradigm. So we have some data here from the healthy controls and then the people with Parkinson's. And what you can see is that beta desync is not as strong. So we have a significant reduction in our beta desynchronization in our patients to what we do in our healthy controls. And I'll go through this very quickly. So some of the really exciting stuff that we also have done is imaging children. So this was kind of a Braille paradigm in 27 children. So they just have these Braille stimulators and they just watch a cartoon and then the Braille stimulators get activated. And looking at different age groups, we're able to look actually at how that beta modulation changes in different age groups. So actually now looking at kind of neurodevelopmental trajectories in the brain. Another study has also been looking at the gamma response, so looking again at that kind of circular grating narrowband visual gamma response. And this is data that was collected between Nottingham and Sick Kids. So we have 102 participants in this study, which is really exciting because something that OPMs we kind of need to work towards is getting these bigger data sets now. And so we can actually see this really nice evolution of the gamma response and how that kind of changes with age. So from going from the youngest participant was 2 up to 34 years old, we can again see this really nice neurodevelopment. And so what's next? So what we really want to look at is how far we can push the spatial resolution and sensitivity. So, you know, these simulations have actually suggested that could we rival invasive electrodes potentially in the future? So there's an idea from Alison Nugent's group in NIH about magnetocorticography and using really high density arrays to get kind of similar measurements that we would be able to achieve in invasive measures. We've shown that we can scan children and begin to understand this neurodevelopmental trajectory. And so, like, something that Sick Kids are working on is that they have done this kind of baby SIBS study. So they've taken children with autism and they're scanning them and their younger siblings from very young ages. So there's around a 30% chance, I think, if you have an older sibling with autism, that you will also get a diagnosis. So the idea is that, you know, if we scan those children through time, then we should have around 30% of them a good kind of neurodevelopmental profile of children with autism. And the thing is kind of how far can we push that free motion? So we're already scanning people while they're walking around. So how can we really exploit this? You know, where can we go next with this? Something that we've actually been working with at Nottingham is using looking at MTBI in people who've just come out of military service, and we're using kind of force plates to measure their gait while they actually get their brain scanned. So there's lots of exciting stuff that we can do. And what I think is the most exciting for me is that this technology is now becoming increasingly accessible, and it's no longer just physicists that are using it, but it's getting into the hands of neuroscientists and people who actually understand more about the brain than we do. And so what I'm really excited for is what all of you will do with the technology. And so, yes, thank you for listening, and they're all my acknowledgements to everyone that's involved in this work, and any questions I'm happy to take.
Thank you, that was amazing. Fabulous history of OPM-MEG in Nottingham, and the technology is just so fast developing. That's really amazing to see. Any questions? We are running a bit late, but I think we have time for a couple of questions before we move on to Teams. Yes.
Thanks for listening, John. I want to ask a question about backpack, because if you are bringing the electronic near the headset, is it going to interfere with the signals? Because or are you using any shielding stuff in the bag?
Yes, so that's a really good question. So what we one of the first things that we did when we received it is kind of do measures of how close and how far away do the OPMs need to be from the electronics, and doing things like shaking the backpack and trying to cause as much interference. So we know that we do measure a small amount of interference from the backpack, but we're mostly able to correct for it through using things like the homogeneous field correction and other kind of interference rejection methods. If the backpack is kind of still and it's not moving around, then when you have around, we found about 20 to 30 centimeters away, you basically all effects of it drop off and you don't really measure it anymore. And it's not something, we haven't had issues with the interference as we've kind of started the movement studies, but it was definitely something that we considered.
Last question here.
You mentioned that the noise field, the noise floor is a little higher in the OPM systems compared to squids, but at comparable sensor count, you have much higher SNR. Is that due to being closer to the scalp?
Yes. Yeah. So this was part of what we wanted to explore, was the kind of comparison studies that we were seeing with the whole head. Is we were getting like kind of comparable or a bit higher SNR than the squid systems. So yeah, that's just by the nature of you reduce the distance, so that the field magnitude that you measure is higher, so you get better signal basically.
So it's compared to ambient noise as well?
Yeah.
Okay, so thank you so much again, Holly. All right, and now we move on to the final talk of today by Dr. Tim Tierney. So Tim completed his PhD in medical imaging in 2017, and since then he has worked on the development of the optically pumped magnetometer for emerging magnetoencephalography applications. He is currently a PI at the Department of Imaging Neuroscience at UCL, where he holds a lectureship in neuroscience and a fellowship from the Epilepsy Research Institute. So we will have you very soon.
Perfect. So I can't see the slides on your screen, but you've got them up, yeah?
We can see everything. It's all good.
Perfect. Okay, so first of all, thank you for inviting me, and I'm really sorry that I can't be there with you in person. Unfortunately, things didn't work out. So also I'm going to have to apologize if people have said some of the things I'm going to be talking about before. Yeah, you'll just have to hear them again for a second time. But today, really, what I'm going to focus on is how we get the best out of OPM data, because it's quite a complex data set that you'll be working with. But I think the first thing to point out is that OPMs are great. They open up a really huge number of quite complex applications. I just want to confirm you can see my second slide now.
Yep.
Brilliant. Okay. Such as, and what we want to do at UCL really is focus on how we can harness the advantages of OPMs, namely the kind of wearability and flexible placement that you get from having an OPM system. So using the flexible placement to target complicated brain structures, such as deeper brain regions like the hippocampus and the spinal cord and the cerebellum, but also looking at how we can harness the wearability of OPM systems to look at new and emerging applications such as full body motion involved in dance, but also fully ambulatory MEG systems where people are not moving millimeters at a time, but meters at a time. And of course, as well, looking at things like immersive reality, where in the case I'm showing here, the participant is actually navigating through a vertical space, but actually it's their body motion is determining how their avatar is moving through that space. So you get a kind of a fully embodied personal experience when navigating through these spaces. But the kind of problem with all this is that if you want to get involved in all these applications, you have to be able to answer one quite fundamental question. And that question really is that when you're looking at your data, is what you're looking at brain activity, or could it be interference? And this is an example here of a power spectral density taken from UCL. And you may look at this and see an alpha peak, but unfortunately, this is not an alpha peak. This is in fact just vibration of our magnetically shielded room. In fact, there is no brain in this data set. This is just an empty room recording. And because in London, we're in a very busy city, we have lots of things going on around us and passing cars going by in the London Underground beneath us. And that means the data we get, because we're working with magnetometers, can be very noisy. So examples of the kind of things you might be dealing with depending on your environment will be things like participant motion, if you're doing kind of studies that involve a lot of wearability, like ambulatory motion or dancing or immersive reality. But also you're going to be looking at drift in the magnetic field due to things like passing cars nearby and vibration, and also things like 50 or 60 hertz, depending where you are in the world, and all these mysterious spectral peaks that you will also spot as well in many OPM data sets. So really the kind of challenge is, if we want to focus on these cool and emerging applications, is to actually be able to deal with all this interference so we can just focus in on the interesting brain signals that can reveal so much about human cognition. But this is hard, and it's hard for a number of reasons. The primary reason why it's been hard for us, at least at UCL, has been the fact that our systems have been changing rather dramatically over a very short space of time, where we've gone from having very bulky helmets and very bulky sensors to more lightweight sensors, but cabling that was still quite heavy, to all the way on the right of this screen, where you should see now that, and Holly's done a wonderful job of introducing this, these kind of backpacks where you can actually put the entirety of the OPM electronics on someone's back and have lightweight sensors. So now you can truly realize a fully ambulatory kind of OPM system. And also, I realize it's late in the day over there in Australia, so I've plugged in an image of one thing that is not an OPM system. Hopefully you can pick out which one is not an OPM system from these set of pictures. But this story is not a unique one, and certainly we've worked with Q-Spin over the years for our systems, but there are many other manufacturers out there. And that adds another layer of complexity to this, because, from my mind, and I love getting into these debates, but I really believe there isn't a consensus on what the kind of optimal system design is. And there are many factors to consider, such as different noise floors, bandwidths, closed loop implementations, number of axes, which people have touched on already, but also things like weight, heat, wiring, robustness, and wearability. And all these factors change kind of how and what kind of paradigms you're going to run, and also therefore what kind of interference you're going to encounter. And in one way, this is quite exciting because there are so many different manufacturers and options out there. But from kind of a methodological point of view, coming up with tools and techniques that can help us deal with the kind of different interference we might observe across all these varied scenarios is really quite a challenge. So how do we get the most out of OPM data? And I'm a real big believer here in kind of looking backwards to the past and looking at what we learned from cryogenic systems to see what we can kind of replicate and leverage so that we can truly harness the power of OPMs. And I'm going to use the kind of, I think, advances in cryogenic systems to kind of structure this talk a little bit so that we can see, okay, what do we need from OPMs? What needs to evolve from cryogenic systems? So the first example might be to use gradiometers, which are very common across typical cryogenic MEG systems. You can also use synthetic gradiometers. So rather than a true hardware gradiometer, you could just simply use two magnetometers and subtract the signal from one to the other. You could use things like reference arrays, which are embedded in many OPMs or many cryogenic MEG systems, which help characterize the background magnetic field and allow you to just subtract it from the data. You can do this simply by just subtraction or do fancier things like signal space projection. But what I'm going to really focus on later in the talk is focus on, I think, model-based approaches, such as homogeneous field correction and adaptive multipole modeling, which are techniques that we've been developing at UCL, but kind of frame them against, again, techniques that were developed for cryogenic MEG systems such as SSS. And I'm going to wear my heart to my sleeve a little bit right now when I say that I'm not going to be talking about data-driven approaches, which I know some people are really big fans of. I'm less of a fan of data-driven approaches, just because, again, as I've mentioned already, when we're working with so many vastly different systems that have changed so much in such a short space of time, it becomes really difficult to work with data-driven approaches because you find it's very difficult to generalize their performance across systems. Whereas when you work with model-based approaches, you can actually construct, generative models that can tell you how interference is likely to manifest across all these different scenarios. So let's start with synthetic radiometers, the kind of pros and cons. I think the big one is that they're easy to implement and easy to understand. You simply take two magnetometers, subtract the output from one from the other, and you simply get great performance. And this is a result here from Nardelli et al. in 2020, where they show, in the blue line, you've got the result from their magnetometers, and in the black line, you've got the result from their gradiometers, just showing that the gradiometers have far less noise than their magnetometers or counterparts. So really, simple to use, simple to implement, good results. But on the kind of con side, the negative side, if you are going to construct gradiometers in this fashion, you're going to sacrifice sensitivity by about 40%. And that's just a statistical consequence of the fact that if you subtract one signal from the other and both contain white noise, you're going to amplify the white noise in the output. You could get around this by constructing a true hardware gradiometer, and there are ones that are kind of in development, work from Cook et al. Recently, and hardware gradiometers are possible, but they're very challenging. You'll see this diagram here on the right, which shows the kind of Cook example, still uses two cells that the kind of one laser beam has to pass through. And that essentially means that both cells still have to be working at zero field. So it still has this criteria of we still need to be operating in very low fields, which again makes the deployment of optically pumped gradiometers still, I think, somewhat challenging, but certainly an open area of development. If we look at something like signal space projection, it's based on this kind of fundamental idea that signals from inside and outside the brain, they produce very different topographies. And Holly touched on this a little bit. And over here on the right, you will see an example of two different topographies that you might observe on an OPM system. And one of these topographies is an interference signal, and one of these topographies is a real brain signal. And what you'll notice in the difference is the interference signal is the one on top, and this is this very broad spatial pattern. And that just comes because of typically if interference signals come from very far away, they produce very broad spatial field patterns, whereas brain signals, because they're quite close to the sensors, produces very focal field patterns. So you can distinguish interference from brain signal purely on the kind of spatial topography. And you can do very simple things like doing PCAs of empty room recordings to capture these kind of interference topographies, and then you can very simply regress these from your data. And approaches like these, again, they're really useful, really powerful, because things like signal space projection can model very complex spatial interference. So for instance, if you've got a particular bit of hardware or kit that you really need for your experiment, and that's generating electromagnetic interference, SSP is a really good option actually for modeling that kind of spatially complex interference. And it also has the secondary advantage of being immune to fixed errors in calibration. And this was definitely a big worry in kind of earlier OPM systems where the calibration really was not comparable at all to SQUID systems. But it's less of a concern now as OPM systems now have quite good implementation of kind of closed loop recordings. But while all this sounds great, there is kind of this one fundamental problem with something like SSP, and that's, does the kind of interference you measure in your empty room recording generalize to the experiment you want to do? So if your interference changes over time, it's not going to work. But also if it changes over space, it's going to struggle. And when we're moving towards really fully ambulatory MEG recordings, it becomes very difficult to develop training data that would generalize to every single point in space inside your magnetically shielded room. So if we kind of consider these kind of ideas and approaches that would be very typically used in cryogenic systems, we can kind of come up with a bit of a wish list for the kind of qualities and properties we would want for any methods we would deploy in an OPM system in order to improve our ability to model brain signal. So the kind of things we would want as a kind of a wish list would be, we'd want the performance of a gradiometer, but we wouldn't want to pay this noise penalty. We'd want to have an approach that would generalize while someone is moving around an environment. And something, again, that was very important for earlier OPM systems was for these methods to be stable and useful at low channel counts. Because in the early days, we didn't have a lot of channels. So it was important to develop methods and models that worked for these low channel systems. But that's now less of a concern as again, I think Holly mentioned, you know, systems now are approaching kind of hundreds of channel marks where this becomes less of a problem. So to kind of meet these criteria, we developed an approach called homogeneous field correction, where we simply, you know, had that very simple idea that much of the interference in magnetometers experience can be modeled as this kind of spatially homogeneous magnetic field. And the model for this is really, really simple. So let's say on this diagram on the right here, you have a field across the head as symbolized by this blue arrow. And this nice schematic here shows some OPM sensors, and their orientations are indicated by these black arrows. Now, all the homogeneous field correction does is says very simply that the magnetic field that you will see at the sensors is linearly related to the sensor orientation. And just what this means is that basically, if your sensor orientation is nearly parallel to the field, you'll see a big signal at that sensor. Whereas if that field is orthogonal or perpendicular to your sensor orientation, you'll see very little field. So very, very simple model. And it only requires 3 degrees of freedom to implement. So certainly helps with that working on low channel count systems. And also quite importantly is the orientation only matters relative to other sensors, not relative to the environment. So that means you don't need to update the model as one moves around an environment. So again, it kind of generalizes as one moves, which is a big important criteria for us at UCL. We've done some very simple kind of empirical comparisons versus things like SSP and kind of constructing synthetic gradiometers here. And this, you know, this is only one case, so you know it's not conclusive, but it's useful for looking at the kind of theoretical properties I discussed before and seeing how they all stack up. So the graph here shows shielding factors on the y-axis. And basically, shielding factors are just how much environmental interference you're removing from the data. So bigger is better. And what's important to know is this dashed black line here is the line which above this you're reducing interference. But below that line, you're actually increasing the noise in your data. So you really always want to be above that dashed black line. So I think some of the first kind of encouraging things is certainly at low frequency, you will see homogeneous field correction and these synthetic gradiometers are actually performing really quite comparably. So again, we're kind of getting that performance we were looking for of a gradiometer, which is really cool. But you will notice that we're doing this without this white noise penalty. So you will see that HFC is always above this black dashed line, whereas in contrast, if you look at your synthetic gradiometer, you will see it dipping below this dashed line, and you'll see in the limit at the high frequencies dipping below by about 3 decibels. And that's exactly what you'd predict from theory, this kind of 40% increase in white noise. And again, as I mentioned before, because the model is only determined based on the relative orientations of the sensors to each other, not the environment, the model generalizes as someone moves around an environment. And it works for low channel systems. And worth mentioning when you compare against SSP, that this data set was taken while someone is actually moving around an environment. And you will see that while HFC and SSP perform very comparably at high frequencies, you will see in the lower frequencies in the kind of vibration region and kind of emotion region, we're not getting as good performance between SSP and the HFC because the SSP just isn't quite generalizing to the different locations in our room. We also looked at, empirical examples, not just looking at the shielding factors, because one way to increase your shielding factor is just to obliterate brain signal. So you need to always check that whatever methods you promote are not just reducing field, they're also preserving and then potentially enhancing the SNR of actual brain signals. So over here on the right, I've got the example of just a very simple auditory evoked field paradigm. And we would expect to see responses at roughly 100 and 200 milliseconds post stimuli. And I think if you look at the eye of faith, you can kind of see those responses, but they're really not super clear. However, if you use this kind of homogeneous field model, which again only requires these 3 degrees of freedom, once you apply that, suddenly you can massively amplify the SNR of the response in your data. which is really very encouraging for us in what we wanted to do, which is really quite exciting. Now, while talking about positives, I think you also should mention, the negatives of your method and how and when things can go wrong. And really, I think the big one is that HFC and a lot of the methods I'm going to talk about, they do depend on your system design and what kind of system you have. And it's important to characterize that. And again, as Holly mentioned, if you've got OPM systems, you can measure not just one component of the magnetic field, but many components. You can measure up to 3 components of the magnetic field. And what we found is when we use HFC in simulation, and these brains here, what they represent is how much signal HFC could potentially remove from the brain, so interesting brain signal, when applied to different array configurations. And what we see is when applied to either a purely radial system or a system that has purely tangential sensors, you can see that as you go deeper in the brain, we start to remove signal. And this in a way is very unsurprising. It's very similar to what a gradiometer would do, where it's really good at preserving cortical sources, but actually will suppress deeper sources. So in some ways, I mean, not a surprising result. But what was a surprising result for me, at least, was that when we simultaneously used multiple measurements of the magnetic field, so we used a dual axis system, we noticed we really didn't get the signal suppression at all. You will see in the brain, we're always in that kind of yellow region, which is seeing very little signal attenuation. So it's implying that we can get a very good separation between brain signal and interference, which is really, really encouraging. Now, I was new to the world of MEG and OPM, so I found this result really surprising, but I think if you knew your MEG physics, you probably wouldn't find this result super surprising. But this result is important because it really does affect how you design your system and what systems you choose. And I think, Matt Brooks followed this result up in 2021, where he looked not just at dual axis systems, but triaxial systems. And he showed something really interesting, where basically he showed that for triaxial systems here in red, so you measure 3 components of the magnetic field, if you increase interference in simulation, you don't change localization error. So basically kind of showing with beamformers at least that the performance of OPM systems, triaxial OPM systems, was reasonably unimpaired by interference when it comes to localization error. Whereas in contrast, single axis systems that only use a radial design, as the interference increases, are really confounded and reduce their kind of spatial localization ability. So does that mean that we need more axes? Is that really the conclusion of kind of these studies, that we need always to have a, let's say, a triaxial system? Well, Schofield and al., a really interesting recent simulation study, has replicated this result in kind of, independently, where they've shown again that if you look at dipole localization error and compare single axis systems versus biaxial or dual axis systems versus triaxial systems, when you do source localization, you get the best localization accuracy with your triaxial systems. So that must really mean, right, that we definitely need triaxial systems. Well, actually, the story is a lot more complicated than that. Because the other really good thing this study by Schofield and al. Has done is not just look at source localization and not just look at kind of spatial filtering, but has looked at both in combination. And when you look at both in combination, let's say things like HFC with source localization, the story changes a bit, quite dramatically, in fact, because this is just an example that they used HFC with their source localization, but they showed that basically that if you're willing to use these spatial filtering techniques, all types of OPM arrays can perform really well in terms of their localization accuracy, which I think is a really positive result for the field, because it means that these software methods that we've been developing allow for kind of harmonization across systems, allow you to actually compare systems and say, well, the performance of this radial array will be very, very similar to this triaxial array, provided I'm willing to use some of these software tools and techniques. And I think it is a really nice example of how these software methods we've been developing can really, I suppose, be that changing factor in getting the most out of our OPM data. Okay, so that's some of the kind of simple models out of the way. Now we're going to move on to talk about some of the more mathematically complicated models, in particular signal space separation, which was developed for cryogenic systems, specifically Megan and Electa systems. And it uses what's called a spherical harmonic model to separate brain signal from interference. And essentially what it does is it fits a sphere inside your array, and then essentially says anything within this sphere we're going to say is brain signal and retain that signal, and anything outside of that array we're going to say is interference and reject that signal. And there's a lot of good reasons we should want to use a method like this for OPM recordings. The kind of main advantages would be that, again, the model does not change as someone moves. It only requires that the sensors are fixed in position and orientation with respect to the brain. So if you can have a fixed helmet, you can use this method as someone moves around, which is really quite exciting. You don't need off-scalp sensors or reference arrays to create your model. You learn everything from what's on the head already. You don't need to know anything about the participant anatomy, and also will reduce the white noise in your data if you oversample, which is, again, quite an important thing because, again, as Holly mentioned, with some of these OPM systems, it's quite hard on the hardware side to reduce white noise. So if we can do anything on the software side, that's really important. But one kind of fundamental question I think that needs to be asked is a method like this going to be valid for use with OPM systems? And the kind of unfortunate answer is that it's very, very complicated. This is some work from Zhdanov et al., which they looked at the kind of noise levels that you get when using SSS with OPM systems. Particularly this example is for single axis arrays. And what they see is that not only does SSS not decrease the noise in their data, that it actually, in fact, amplifies the noise in their data. And you can still see, even at hundreds of sensor numbers, you're still getting noise amplified by a factor of 10, which is really not ideal for any MEG system. But they did something quite cool where they said, well, okay, we've got this problem, but actually we can use this problem as a cost function. So if you're able to change your system, what you could do is optimize the orientation of each individual single axis sensor in order to minimize this noise amplification factor, which is a really cool kind of approach to take. But the downside is if you've got a fixed system that you can't change, then this approach isn't going to work for you as a a consumer basically who already has bought an OPM system from a certain manufacturer. The other problem is kind of the actual model itself, which is based on spherical harmonics. We looked at this in detail a number of years ago, where we looked at how well these spherical harmonic models explain signals both in SQUID data and in OPM data. And if you look at these brains here, well, basically, the more yellow the brain is, the better the signal, or the better the model is at explaining signal in that brain region. And the bluer it is, the worse it is. And I think what you can see straight away is, unsurprisingly, the model works really well for SQUID systems. But what you see is something systematic starts to go wrong in the OPM systems, where you start to see at the front and back of the brain, you start to get an under-explanation of the data. And also, as you get closer to the tips of gyri, you also see this kind of under-explanation of the data. So what's going on here? What's happening? The answer, in a way, is actually quite intuitive. And that's the fact that these spherical harmonic models require that the minimum volume sphere that encases your brain is inside the scalp surface, that your sensors are not inside that volume. And unfortunately, if you've got an on-scalp system, there's very few head shapes and brain shapes that allow you to actually achieve this criteria. So we thought about ways we can adapt this, and one of the approaches we're thinking is changing the geometric model. So instead of working with spherical harmonic models, we're looking at things like spheroidal and ellipsoidal harmonic models, which allow you to change the geometry so that the geometry, in this case a spheroid, will fit inside the scalp surface and not intersect with the scalp surface and provide a more or a better explanation of the neural data. So that's what we've done. We've developed this approach called adaptive multipole modeling, which, as I said, is a solution to Laplace's equation in spheroidal coordinate system as opposed to a spherical coordinate system. And that kind of solves the problem of the brain signal model not being ideal. But also, we've done our very best to make the model, absolutely stable. And I mean stable across every single type of system you can possibly design. So that you don't need to change your system. The method will adapt to your system and produce a stable response regardless of what your system is. And that was really, really important for us because, again, we work very closely with many different people who have very, very different kinds of systems. And I'm going to show some maths in the next 2 slides, but I'm not doing this to go through the maths, just to show you that there's a really solid theoretical foundation to kind of the claims that I'm going to make. If you want your method to be stable, you're going to want your projection or your method to basically have changes in the output that are smaller than the input. So essentially, if some noise is added to the system, you want not to be a huge change in the output of your method. You want there to be, if you add small amounts of noise, there's small amount of changes in the output. And you can guarantee this property if your method or your projection is what's called an orthogonal projection. And you can prove that analytically. And again, if anyone's really interested, we can go through that afterwards. But the important point is that if you can essentially prove this point of your method being an orthogonal projection, and this is these criteria down here, then you can actually claim that your method is stable across any system that anyone can possibly create, which is a really powerful claim. And again, we're not going to go through the maths here, but again, I just want to show you that for AMM, you can actually go through and prove all these properties analytically and say, well, actually, I know that this method is just going to work on whatever system it's thrown against, which is really quite powerful. In contrast, for something like SSS, you just can't prove this, which means that the method is not orthogonal and therefore it can't be, or is not guaranteed to be stable for all systems. So then you have to work really hard to try and make the method stable. And you can do things like, changing the system, as I've already talked about, increasing channel number, which is Holly's talked about, reducing model orders, or approximating things like orthogonal projections with data-driven approaches. Okay, so that's the maths out of the way. Let's look at some real empirical data demonstrating, again, some of these theoretical properties in practice. And this is some real data, some noise spectral densities taken from a dual-axis system comparing both TSSS and AMM. And what you can see in the AMM data versus the filtered data, you don't see any increase in that noise floor. But in contrast, in the TSSS case, you actually see the noise floor has increased, exactly in line with what we would predict from the kind of theory of the SSS not being stable for every system. Now, of course, as I've mentioned before, you can't just look at power spectral densities because, again, you can get good results just by eliminating brain signals. So you always have to check that you're not eliminating any brain signal. So we looked at kind of an empirical example of looking at a simple 4 Hertz flickering checkerboard paradigm, where we should see a very strong 4 Hertz response in the brain. And in fact, that's exactly what we do see in the AMM category. You can really clearly see these 4 responses happening a second. And in the topography, you can see really clear results in the visual cortex. Unfortunately, in the SSS case, because of this problem of projector stability, you just don't see this result very clearly at all. And one of the questions I always get asked about this method, because I've shown the kind of results and the validation has all been at a sensor level. So people always ask, well, what happens at the source level? How do these methods interact when you do source reconstruction? And thankfully, that paper I mentioned earlier and that Schofield et al. Paper, they've done a really, really comprehensive analysis of different spatial filtering methods and how they compare and how they interact with source reconstruction methods. So they've done a comparison already with AMM and TSSS, and shown that AMM has about 33 to 400% better localization accuracy than something like TSSS. And again, this all kind of comes down to this projector stability, which is really quite encouraging. Right, so that's theoretical and simulation stuff out of the way. Let's look at kind of real world data now, and something that's quite important for me is kind of the clinical applications of these methods. Sarah mentioned earlier that I'm funded by Epilepsy Research Institute, and really my fellowship is about developing the technologies that could be employed in a clinical setting and how we, again, get the most out of the data we've got in these clinical scenarios. So I want to show you kind of 2 very different clinical scenarios here. One is a single-axis closed-loop system in a busy hospital, specifically the Children's Hospital of Philadelphia. And they wanted to do some benchmarking of their new system that they'd bought. So they did very simple auditory evoked fields. And the second example is a pediatric patient with epilepsy. And we're looking at a dual axis open loop recording. And in this case, we were doing some language mapping. So we wanted to, work out where in the brain kind of the language is represented so we could inform the surgery this child was going to have. So while these are both 2 very different scenarios, they're across different continents, they have different systems, different implementations of closed loop, different number of axes, all these things are very different. What was common was both scenarios had very noisy data because they were corrupted by a lot of low frequency interference. In Philadelphia, it was because they've got really busy hospitals, they have a lot of drift. And in the pediatric epilepsy patient, it's because they simply were moving a lot and they were unconstrained, and that led to a lot of low frequency motion artifact. And that was particularly important in this case because we were looking for like an N400 or an M400 response, which is very low frequency. So we can't just, apply a filter and try and uncover these signals. If we apply our filter, we'll lose the signal of interest. So we need to rely on these kind of spatial filtering methods to get at the underlying brain signal. So when we applied AMM to these data sets, what again was in common is we were really beautifully able to recover these responses. Again, in the Philadelphia case, of these really lovely auditory evoked fields, and in the epilepsy case, we can really clearly see the first 100 millisecond response into the visual stimulus. In this case, it was a picture naming paradigm, but also this kind of M400 response, the kind of semantic response that we're really interested in, that we're going to use for our source localization of our language network. Okay, so that's some clinical examples. The last example I want to finish with is our fully ambulatory MEG system. And this really has only been made possible by the kind of advances in hardware that Holly was talking about, where now all the electronics for these OPM systems can be put in a backpack that someone can wear while they move around an environment. So indeed, hold on, just trying to get this video to play. Oh, having some problems. Perfect. Okay. And you can see here now we have our subject who's fully moving around an OPM shielded room, and we're now talking about not moving millimeters, which you would typically be constrained to in, let's say, a cryogenic MEG system. We're now talking about moving meters at a time. So, maybe 1,000-fold increase in the kind of motion we can work with. And that's not to say we don't get motion artifact. We definitely do. If you actually look at the raw data, what you will see is that we're getting 5 to 10 nanotesla peak-to-peak changes. And if you're not familiar with OPM data, these changes are about 10,000 times larger than kind of brain signals we're interested in. So to validate we were actually getting useful signals, while this person was walking around the room, we again played some little tones to their ears, so some auditory evoked fields, and that we should be able to see kind of when we look at this data. But perhaps unsurprisingly, beneath all this motion artifact, that if you just average this data together naively, you wouldn't see much of anything. You'd just be looking at the kind of motion artifacts. However, again, when you use these spatial filtering methods I've been talking about, such as AMM, you're able to beautifully uncover these responses. I'm just again highlighting how this interaction between changing hardware and kind of evolving software has allowed us to focus on applications that just wouldn't be possible with cryogenic MEG systems. Okay, so I kind of rocketed through a lot of that, but I appreciate it's the end of the day for you guys, and you probably want to get your drinks and ice creams. So I'll just end it there. And as a quick summary, just want to highlight that there are now OPM-specific signal processing tools available to maximize your performance across kind of any system. They're available in many of the popular programming kind of toolboxes in SPM and in Fieldtrip. And I think even now there's some kind of SPM Python bindings that allow you to use some of these tools if you're using something, let's say, like M&E Python. So that's quite exciting. But also I think something that's really positive for the field is that if you're willing to use a lot of these software techniques, it's been shown that all systems can perform really, really well in terms of source localization. It just requires you to think a little bit more about how you analyze your data. And I think that's a really positive step for the field, because it means we really can compare results across systems and across labs, which can be quite tricky when everyone has different systems. And finally, just like to say, that OPMs now are opening up huge novel applications for MEG that involve whole body movement that just wouldn't be possible with cryogenic systems. Okay, so with that, I would just like to thank all the huge amount of people who've been involved in this work and all the funders who made it happening. And also I'd like to thank you guys for all listening at the end of the day, which I know must be quite challenging, to a dense talk on software and maths. But I thank you all for listening, and I'm really happy to take any questions that you may have. Thanks, everyone.
Wonderful. Thanks so much, team. It's Marta here. So we are running a bit late in our schedule, but I think we can have 2 questions. And again, thanks so much for calling in at quite early. What time is it in London at the moment?
Oh, it's only 9 a.m. here, so
9
it's like
a.m.
normal work.
Okay, okay, still. All right, so questions for Tim? Yes, yes, yes. We don't have a microphone, but maybe speak loud.
Can you hear me? Well, can you hear me?
No, he can't. Maybe come over here. Okay. Tim, we've got a question.
Yep.
It's coming up. We just a few seconds. Okay, there we go.
Okay, thank you for the talk. I'm curious about the figure just in on this page. So the localization area you come across 3 axes. This figure, yeah. This shows, the single axis shows much better accuracy than 3 axes. So what's your comment on it?
Oh, I think if you look at means and medians, sometimes you can be a bit kind of misleaded. I mean, if you look, these are violin plots, so they can show you the variability as well. So I think you're not really seeing a massive difference. One thing that's probably worth considering is in this study, again, I wasn't involved in the study whatsoever. I don't think they've updated the lead fields after they've applied these methods. So I still think there's something of a confound in the modeling, which might play into this as well. But I think you're talking about very small differences between systems to small relative to the variability they observe. And I think with this confound of the lead fields, okay. I wouldn't over-interpret that result as a meaningful difference.
Okay.
But having said that, I think one of the other claims these authors want to make is that because there is a white noise penalty for going from single to dual axis to triaxial, you might actually expect, if you can clean up the noise in a single axis system, to get the best result out of a single axis system. So that's one of the other messages they want to kind of get across.
Okay, good. Thank you.
Any other questions before drinks? No? Daniel? Yeah, last question, Daniel. He's just coming down to where we've got the microphone so you can hear him, Tim.
The name.
Tim.
Hi, Tim. Can you hear me?
Yes.
Yeah. Actually, I want to ask a question about the backpack study in which participants was exploring the environment. And I was just curious, when participants was exploring the environment, the whole brain was active because he was visualizing his he was making decision. So is it easy to differentiate between noise and when the whole brain is interacting with the environment?
I think it's a really good question. I suppose you could say, because we're doing an evoked paradigm here, anything else that wasn't time locked exactly to our stimuli is going to increase the variability. So in theory, what you're saying could be true. But I think the really positive way to look at that is there's now more signal to model, right? So that if you're getting more complex input, you're going to get more complex output. And I think that just opens up the opportunity to be developing new analysis and modeling methods to model all that extra variability. So I can see that, I think from one perspective, you might look at it as a confound, and certainly could be seen as a confound in this study. But I think the really positive way to look at it is there's a whole lot more we can now do and model when using these more naturalistic paradigms.
Wonderful. Thank you so much, Tim, for joining in online, and I hope we get to meet in person at some point. We'll bring you to Australia.
Are you coming to MEG UKI? Did I hear?
I am coming to MEG UK in
so I think we'll probably see each other there then.
Yeah, that's right, for sure. Okay, well, I'm sad that you can't join us for drinks, but we'll go and have a drink, and you can have your coffee maybe. All right, so guys, before let's thank Tim again. So I just want to end to say thanks so much to our speakers, Sophie, Holly, and Tim, for doing such a wonderful job of teaching us all about OPM-MEG. Also, thank you to our volunteers that helped with the demos, Elise, Tracy, and Lila. over there. And finally, thank you to Sarah, who has done all the logistics and got the table full of yummy foods, and even ran out to get more when they ran out. And thank you all for your attention and for your engagement, and I hope to see you in the lab at some point. Thank you.